inference to improve performance and reason about its behavior statically while maintaining the probabilistic programming paradigm. So let's start with a motivating example. Here we have a radar tracking problem where we want to estimate the distance and altitude of an aircraft as it's flying using radar measurements. And how can we do this? Well, one method is to use Bayesian inference on a probabilistic model, and one tool that makes it easy to express probabilistic models is probabilistic programs. So that's right one for our situation. So first, since we want to model the distance and altitude, we instantiate random variables drawn from probability distributions. For example, here we have the variable x representing the distance being drawn from a Gaussian distribution, and its mean is the previous distance value. Here we write that as x0. And the variance is another random variable q, which is itself drawn from an inverse gamma distribution. Since we want to know the values of x and alt, we return that as the final expression in a tuple. Next, we want to condition our probabilistic model on radar measurements in order to actually perform the inference. And this conditioning is done with the observe keyword. So the first argument is the distribution of the random variable that we want to condition. Here, the first observe assumes the distance measurement is drawn from a Gaussian distribution centered around the true distance. And its variance is the random variable r, which represents the white noise inherent in radar measurements. The second argument of the observe keyword is the value that we want to condition the observed random variable to be. So in our program, those are the free variables xops and aops, which represent the actual data itself, which are also the inputs to the program. Lastly, when the aircraft is flying at low altitudes, when it's like close to the ground, the aircraft experiences additional noise modeled with the variable other. The if expression branches on the altitude value to use the sum of r and other when in low altitudes and just r otherwise. So altogether, we've created a probabilistic program that encodes this diagrammed probabilistic model for our problem, where the yellow nodes are the latent variables and the white nodes are the observed variables. And the program should output the distributions of x, which is the distance, and alt, the altitude, of the airplane as it's conditioned on the input data, which are xops and aops. So now the question is, how do we actually execute this program to achieve this? Ideally, we like to get an exact answer. So using exact inference to symbolically compute for the closed form solution would do this. But these type of algorithms can only solve problems that have nice properties, such as linear Gaussians or conjugate distributions that actually have analytical solutions. And in this case, in our program, there are no analytical solutions that we know of. So what can we do now? Well, we can use approximate inference instead. An example of how this type of algorithm runs is first you would have multiple executions of the program, which are called particles. We execute the program in parallel, sampling each random variables as they are encountered. And conditioning is performed by weighing the particles based on the likelihood of the observed data. Here we indicate that by the sizes of the boxes. And the final solution is the weighted sum of the particles. This will get us an approximate answer to the inference solution. And these methods are great because they can solve all types of problems. The caveat is that the solutions can have high error with limited execution time. And resampling a new set of particles based on the weights at certain checkpoints can help lower the error in the solution. This type of approximate inference is called particle filtering. However, depending on the program, this still might not be enough to lower the error. So a third type of inference seeks to further address this, and they're called hybrid inference. So hybrid inference combines the flexibility of approximate inference with the accuracy of exact inference. And how this is achieved at a high level is the algorithm analytically solves parts of the problems and samples random variables when it can't make any more progress symbolically. For example, in this program, the algorithm determines that the variable q doesn't actually need to be sampled, so it keeps it as a symbolic expression. For the purpose of this presentation, we don't need to go into the exact details of how the algorithm makes this decision, just that it does some computation to figure this out. Putting it all together, a hybrid particle filtering algorithm would do the same thing on a bunch of particles and perform particle filtering the same as before, except some of the variables are kept as symbolic expressions. And in the end, we still get a solution, and the solution generally has reduced error. There's several of these hybrid particle filtering techniques for probabilistic programming languages, such as semi-symbolic inference, delayed sampling, and sequential Monte Carlo with Boolean propagation. However, there's a particular detail to hybrid particle filtering I'd like to point out, which is that there can actually be multiple different choices of random variables to be kept symbolic or sampled. We call each of these an inference plan. Here we have two different plans for our example program, one where x is kept symbolic and one where r is kept symbolic. Different inference plans can produce different inference accuracy for the same runtime. Here we have the error of the estimated distance across 100 time steps for each of these plans while given the same runtime constraint. So we can see that the symbolic x plan is slightly more accurate. However, different inference plans can also make different variables more accurate. Here, symbolic r is more accurate for the altitude. And choosing which representation to use then depends on 1, the probabilistic model, and 2, the problem constraints imposed and the metrics used by the developer to evaluate the program. And hybrid inference algorithms use heuristics to decide which inference plan to use. And while these heuristics do take into consideration the probabilistic model given, because that's the program itself, they are oblivious to the developer's problem specifications, so they might select inefficient representations. Additionally, there might not even be a plan that achieves the best performance across the board, such as in our example. So even more so in cases like this, developers need an interface to choose an inference plan to achieve better performance based on their system considerations. So I will now present such an interface. So our interface is composed of two parts. One, the distribution encoding annotations that enable developers to express representation choices of random variables. The second part is satisfiability analysis, which I will get into later. First, I'll present the annotations. So we want to tell the inference algorithm in our program to keep R symbolic here. So what we do is annotate each random variable with either symbolic or sample to specify the representation of the variable that we want. So here, R is annotated with symbolic, and everything else is annotated with sample. When a random variable is annotated with sample, the program runtime will sample the random variable upon instantiation to satisfy the annotation. Here, the sample annotation causes Q to be sampled and collapse to a constant value. And this goes for all the other sampled annotated variables except for R, which is annotated with the symbolic annotation. The symbolic annotation asserts that the random variable must not be sampled during the execution. It's an assertion, not an action. And sometimes this assertion can be false. So in our program, in some executions, the algorithm doesn't know how to perform inference without sampling R. So this means that the symbolic annotation is just unsatisfiable. And in this case, what the program can do is it can abort midway, or it can issue a warning and sample the annotated variable anyways to force the execution to continue. This means that the program is deviating from the annotations, but at least the program will continue running and produce a result. The trade-off of this approach is that the program is now implementing a different inference plan, which can have performance implications. So what that can look like is, for example, in our program, when the aircraft is flying at high altitudes, the annotations are satisfiable in both the symbolic X plan and the symbolic R plan, which gives us the error plots that we saw earlier. But in a different flight mode, when the aircraft is descending, the symbolic R plan has an unsatisfiable annotation because the input data is in a different regime. So now we see a much different performance result compared to the last slide. Specifically, the symbolic R plan has a significant error spike in the distance compared to the symbolic X plan. And this is beyond what's acceptable for our problem constraints. So as a developer, we wouldn't want to use the symbolic R plan. The bottom line is, to correctly reason about and choose inference plans, developers should know which plans do not ever have unsatisfiable annotations and which plans might in some executions. And so to help developers do this reasoning, we also developed the inference plan satisfiability analysis, which statically infers whether a given set of annotations are satisfiable for all possible executions of the program. The analysis is an abstract interpretation with an abstract domain over the symbolic expressions used by the algorithm. This allows the analysis to approximate how the algorithm makes decisions about whether to sample random variables. So let's take a look at the program that we've been looking at with the symbolic R plan annotations, which we know have unsatisfiable annotations in some executions. So first, the annotation notes that R is a symbolic random variable. whereas other is a constant value because we know that it's sampled. Then in the if expression, r plus other is noted as just the sum of r symbolic variable and a constant. Because r is symbolic, the summation itself is also a symbolic expression. The else branch is just the variable r. But to summarize the two branches, the analysis would infer that this v is some generic expression that references r. And finally, the analysis notes that the program is conditioned on a Gaussian distribution with these symbolic expressions as parameters. And the analysis will use these abstract expressions to decide whether the symbolic computations that is required to keep r symbolic can always be performed. And in this case, they cannot. So the analysis would return unsatisfiable as the judgment, which is what we want. On the other hand, with the symbolic X-plan in this program, the analysis recognizes that the mean of the conditioned Gaussian distribution is just the symbolic variable x, and the variance is just a constant. So it also recognizes that the algorithm can always perform the required symbolic computations that allow x to remain symbolic. So the plan is judged satisfiable. So that's the annotations in the analysis. And we also developed Siren, a programming language that implements the various hybrid particle filtering algorithms and supports the inference plans using the annotations and the analysis. So that's our interface. Additionally, we performed an empirical evaluation to answer two questions. First, does using inference plans offer better runtime and accuracy? What we're really asking with this question is there some set of annotations that can improve performance from the default behavior of these algorithms? So using 3 different hybrid particle filtering algorithms, we evaluated every satisfiable inference plan for each benchmark on the basis of runtime speedup and accuracy against the default. To summarize the result, for each benchmark and algorithm, we computed the geometric mean of the speedup across variables. So if there is a bar, that means there is an alternative plan that is faster than the default behavior. So as we can see, for all 3 algorithms, alternative inference plans are often faster than the default. Overall, it provides 1.76 times speedup on average. In terms of accuracy, we did something similar. We computed the accuracy ratio achieved by the best performing plan to the default plan for each variable. Then to summarize, we computed the geometric mean across the variables for each benchmark and algorithm. And as before, we can see that the custom inference plans also improve accuracy for a given runtime constraint. Overall, it achieves 1.83 times better accuracy. For a detailed breakdown of the performance result comparison, please see our paper. But to answer our question, yes, inference plans do offer better runtime and accuracy. And the second question we want to ask is the satisfiability analysis precise in practice? So we ran the analysis on a suite of benchmarks. For each benchmark and algorithm, we counted the total number of satisfiable inference plans and the number of satisfiable plans that were identified by the analysis. So overall, we found that the analysis perfectly identified all the satisfiable plans in 27 out of the 33 settings. And in 32 out of the 33, it achieves at least 75% accuracy. So overall, it's pretty precise in most cases, with a few exceptions where in tree and wheels, the joining of expressions just made them too imprecise for the analysis to definitively say that a variable annotated with symbolic will never be sampled. Another source of imprecision is from aliasing, which we observed in SLDS. Lastly, in SLAM, we saw imprecision due to widening we had to perform to ensure the analysis does reach a fixed point. Rather than that, the analysis was precise in practice. And so to conclude, to wrap up, using inference plans, programmers can optimize a program for better inference performance while maintaining the probabilistic programming paradigm through our simple annotations and our static analysis. They don't have to write their own inference procedures, and they don't need to maintain a deep understanding of the hybrid inference algorithm they're using. So in our work, we focused on hybrid particle filtering. However, the need to optimize programs for better performance exists for other types of algorithms as well, and so does the need for a similar interface to inference plans in those cases. Please take a look at our paper for more details, and that's it for my talk. Happy to take questions.
Great, thank you. Any questions? Oh, wait a minute.
Just a very quick question, because I didn't quite get it. The The inference showing what is satisfiable or not, what is the exact guarantee that it says? Is it guaranteed that if it says satisfiable, then it really is?
Yes.
Okay, thank you.
Thanks for the great talk. So a lot of these algorithms without annotations sort of are optimistic. They try to make something symbolic until maybe it can't be. And I'm wondering if you thought about, having a third annotation that says, like, let the system decide, try to be symbolic if it can. If it can't, too bad, prefer the ones that I annotated as symbolic. And what do you think that the system, either the implementation or the static analysis could be extended to handle that kind of annotation?
So what we currently do is that if you just don't annotate it, then the system will just decide and referencing what it has already. But it doesn't go out of its way to make the existing annotations work.
Great. Thank you.
Any other questions?
In the evaluation where you showed the speed up and accuracy improvement, how did you decide which analysis plan to pick? I mean, how did you decide which variables to annotate? Did you try a bunch? Is that the best over all of the options?
Yeah, so what we did was we did a enumerative annotation. We just did symbolic and sample for every instance that is like drawn from a probability distribution. And then we found the ones that were actually satisfiable. Like if it's not satisfiable, we didn't run a performance evaluation on it.
Practice, what is the workflow you imagine that a developer would use? Because like a priori, I don't know which ones to make symbolic or not. So what do you like? What is a good strategy?
So we generally assume that there's some heuristics that you do know as someone who's writing this model. So you would try some annotations, and and you run the analysis, and it would just eliminate the ones that don't work. So you could do the same thing as I did doing the evaluation, where you have a script that enumerates all of them, and then eliminate the one that don't work, and then based on your own like evaluations and metrics to pick which one makes the most sense.
All right, I think we have time for one more question, if there's anything. If not, let's. Oh, sorry.
So your analysis checks whether it's satisfiable for all possible with probability 1. But in your example, there were regimes where it was very low probability of breaking into sampling. So how do you expect developers to think about, like, if the analysis fails, should I still try running this anyway? And do you think there are relaxations of the analysis that could be useful?
There's definitely different designs to inference plans than ours, for sure. But I think the main point is that even if it's low probability, you might still want to know. And I assume that when you're writing this program, you have some kind of intuition of how likely this is. Like for our case, like the example program was, your plane's got to descend at some point, right? So.
Great, let's thank Ellie again. All right, so next up we have Fabian, who's going to talk about guaranteed bounds on posterior distributions.
Is it on? Yeah, okay. Cool. Yeah, so let me get started with a simple probabilistic puzzle. So suppose you have a fair 6-sided die, and you throw it repeatedly until you get a 6. And during your throws, you only observe even numbers. What is the expected number of throws, including the 6, conditioned on this event? Now, this is a fairly famous puzzle, and a lot of people get it wrong the first time they hear it, because they assume it's the same as throwing a 3-sided die. Yeah, so maybe a good way to formalize this would be to write it as a probabilistic program, which you can do like this. So we have 2 variables, number of throws, and variable for the die. And as long as the die is not 6, we sample the die, observe that it's even, and increase the number of throws by 1. So even though this is a simple probabilistic program, it poses a couple of challenges. For example, it has variables with infinite support, because the number of throws is unbounded. we have observations and conditioning, and unbounded loops. And it turns out that no existing tool exists, but there's no tool in existence for analyzing this automatically and rigorously. So what techniques are there? We've heard in the previous talk already that there's exact techniques, which give you a precise result. But this is often intractable or requires extensive user annotations, especially if you have loops, you need to provide loop invariants. On the other hand, you have approximate methods, which are always applicable, but have no or few guarantees. So as a middle ground, we're looking in this talk at guaranteed bounds, which are often applicable and give you hard guarantees. So they will tell you, for example, the posterior probability of the variable x being equal to a is between L and U. Guaranteed bounds were, in fact, the theme of my PhD thesis. And we also had a paper at PLDI 2022, where we motivated them with 2 points. First of all, you can view them as safety properties. So you bound the probability of reaching unsafe states. And you can also use them as a ground truth to debug approximate inference methods. In the previous work, this was a very general setting with continuous variables. And if you apply the same thing to discrete programs, it turns out it has quite a bit of overhead. And furthermore, it could only bound probabilities and not moments and tails. And those are 2 points we address in this work. So specifically, we look at discrete probabilistic programs with variables in the natural numbers, and you're allowed to use conditioning and unbounded loops. And we want to automatically find bounds, not only on probabilities, but also on the moments, like the expected value, for example, and on the tail asymptotics, so how quickly the probability mass decreases. And for this, we have 2 approaches. One is called the residual mass semantics, and the other is the geometric bound semantics, which we'll get to later. But first, let me quickly introduce the programming language that we consider. It's a fairly minimal imperative programming language with a fixed number of discrete variables, which, as I said, take values in natural numbers. We have usual program constructs like branching, loops, observations, and we can increment variables by constant, decrement them, and sample from Bernoulli distributions, so do coin flips. And the events we can observe and branch on consist of comparing a variable with a constant and logical connectives. Quick note on the expressiveness. So the deterministic fragment of this language is already Turing complete. And with those coin flips and the other constructs, we can encode many other distributions, such as all finite discrete distributions, geometric distributions, and negative binomial distributions. Some other constructs are hard to encode, though, for example, a Poisson distribution. So what is the semantics of this language? Well, it's typical for such imperative language to have a transformer semantics. So the idea is that your program transforms some initial distribution on the state space of the variables to the distribution you get at the end of the program. So for example, an event would restrict the initial distribution to the states where the event holds. And similarly, a statement would transform the distribution, for example, by incrementing, like if the statement is incrementing a variable, then the states would be transformed this way, and we would get a result distribution. We usually assume that at the start, all variables are 0. And if you know probabilistic programming well, you've probably noticed that I haven't talked about normalization, but it turns out that it doesn't cause a lot of problems, so we'll ignore it in this talk. What is tricky, though, is the semantics of loops. The loops are the hard part in this setting. So let me quickly explain their semantics. So if you have such a loop, while E do B, we start with some initial distribution mu, and can describe what the loop does with a fixed point equation. So the distribution mu kind of flows in, and then a part of the distribution exits the loop immediately if the loop condition is not satisfied. But some part of it enters the loop, is transformed by the loop body B, and then fed back into the loop again, which gives you this fixed point equation for the semantics of the loop. So first, let's look at how we can get lower bounds for this. This is a well-known technique. We can just unroll the loop a few times, and we will get a lower bound as follows. So we take the fixed point equation, apply it again on the right-hand side, and at some point, we just say the loop will produce a measure that's at least 0, so we get a lower bound like this. So here we did 2 unrollings, but you could do more. This has a lot of advantages. It's easy to compute. In our setting, we only need finite discrete distributions during the computation, and it converges to the true distribution as you increase the unrolling. Upper bounds are harder. So we come up with the following idea. As the probability distribution flows through the program, we can look at the total probability mass. So initially, this will be 1. And then in each loop iteration, some of the mass will flow out of the loop. So we can bound the residual mass that's still inside the cycle if we just take the difference between the initial probability mass that has flown in and the lower bound that we computed with the unrolling. And this way, we can bound the probability of an event S at the end of a program, of the loop, by just taking the lower bound and adding the residual mass, because there's no more mass left, so this will be an upper bound. So this is a fairly simple idea, but it works quite well. So if we apply this to the example from the start, here with 40 unrollings, we are orders of magnitude faster than previous methods. And as you can see, so on the x-axis, we have the number of throws, and on the y-axis, the probability mass on a log scale. So you can see up to the unrolling limit, it's very good, and then we kind of have this flat bound because, yeah, this is the residual mass. Because of this flat bound, we can't get non-trivial bounds on the expected value, because this will just be infinite, because there's infinite support. So we want to find more informative bounds. And for this, let's look at this flow diagram again. And the idea in the previous, for the residual mass, was to look at something that decreases, which will be the residual mass. And now we'll think about what happens if the distribution itself decreases in each iteration uniformly. And even better, if it decreases by a constant factor less than 1. Well, it turns out then we can do something quite nice, which is if we take this fixed point equation again, we can pull out this factor c and move the second sum into the other side, divide by 1 minus c, and then we, ta-da, get a bound on the distribution of the loop. Of course, this condition of this uniform decrease by a factor of c will not be satisfied very often. But it turns out that in many cases, we can find a kind of slightly larger distribution, nu, than mu, which satisfies this condition. So this is kind of analogous to strengthening the inductive hypothesis in a mathematical proof. So just to define this properly, we call this concept a contraction invariant, because the distribution contracts by a factor of c. So we have an initial distribution nu, then a contraction invariant is another distribution nu that bounds mu, and that decreases uniformly by this factor c. And by the same argument as in the previous slide, we can then bound the distribution of the loop on mu using this contraction invariant. Now the question is, how do we find such a contraction invariant? The space of possible distribution is huge, so we have to somehow restrict it. And we have to restrict it to a class of distributions that have non-trivial tails and tails that we can reason about easily. So our first idea was to look at geometric distributions, because there the tails decay exponentially, and that's very simple behavior. And in fact, you can compute the moments in tails easily, but a problem is that geometric distributions are not closed under many operations that you would like. For example, if I increase a variable by 1, it will not be geometrically distributed anymore. So we generalized geometric distributions to something that we call eventually geometric distributions. So we allow them to differ for first few values, for small values, which we call an initial block. So we write this as follows. So EGD, some initial block, and the decay rate means that the initial probabilities will be those indicated in the initial block. And from then onwards, they decay exponentially with rate alpha. We can do this in higher dimensions as well. For example, here we have a 2x2 block, and in one dimension, the probability mass decreases with the rate alpha, and the other dimension with the rate of beta. So this class of distributions has some nice properties. It's still easy to compute probabilities, moments, and tails, because they rely on geometric distributions, but they're closed under many more operations. For example, increment and decrement. All right. So we have to build a semantics that operates on these EGDs and yields upper bounds. And contrary to before, this cannot really be a transformer semantics, cannot be a function, because there may be many upper bounds that are valid. So instead, we defined a relational semantics, PGO, which relates pairs of distributions. So the way you can think about this is the distribution EGD P alpha is related to EGD Q beta. So this is designed to ensure that when I run the program P on this initial distribution, the result will be bounded by the right-hand side. And it turns out we can define this semantics in such a way that this relation reduces to polynomial inequality constraints on the parameters of the EGDs. And this is nice because solving such inequalities is decidable. So for a given initial distribution, we can decide whether there exists an upper bound. So we have a couple more theoretical results in our paper, which I'll just quickly mention. First of all, of course, you want this to be sound. It turns out it is, both semantics. We also have a convergence result. So both bounds converge in total variation distance to the true distribution as you unroll the loops further and further. Terms and conditions apply, details are on the paper. And we also investigated when such bounds exist, because it might just be the case that this system of polynomial inequalities has no solution. And we found some sufficient and some necessary conditions for the existence. So let's see what this method can do for our introductory example. So again, we see the probability masses plotted, in green the exact probabilities, and then I'm showing two geometric upper bounds. This comes back to the talk, as I mentioned before, to the point I mentioned before, that there can be more than one upper bound. And in fact, these two upper bounds have different trade-offs. So the one in blue is optimized for the total probability mass to be as low as possible. And the other one is optimized for the tail asymptotics to be as good as possible, which is why the black line is much steeper than the blue line. But on the other hand, it's worse for small values. Right. So the original question was about the expected value of the number of throws. And so the exact value is 1.5, and our method gives a very tight bound on this in less than a second. And we can also bound the tails. The true tails decay with a rate of 1/3, and we can find 0.34, so also quite close. We investigated the usefulness of the method more systematically. So we collected 43 benchmarks from the literature on probabilistic program analysis and added some of our own. And for 37 of those, so 85%, our geometric bound semantics can find an upper bound. And this includes many examples that could not be automatically analyzed before. In terms of performance, the running time was usually a few seconds or less. For complicated examples, it went up to 5 minutes. The quality of the bounds is difficult to summarize, but I would say it's usually quite tight. But it gets worse for distributions with heavier tails. We also compared with some previous tools. And the summary is that our tool supports more benchmarks and is often faster. So in summary, I've presented to you two techniques to find guaranteed bounds for the posterior distribution of discrete probabilistic programs, residual mass semantics and geometric bound semantics, and introduced some novel concepts such as contraction invariance and eventually geometric distributions, which I hope will be useful maybe in other probabilistic program analysis techniques in the future. Thank you for listening, and I look forward to your questions.
Thank you so much, Fabian. Any questions?
Hi. So you mentioned that you works. So that you identified some of the necessary and sufficient existence criteria. How many? Can you describe how many of these criteria are at least somewhat automatically checkable? So if I have a probabilistic program, can I just look at it and relatively easily see, oh yes, it satisfies or it doesn't?
Easy syntactic criterion, Because, for example, if you look at a random walk, biased random walk, then if it's biased towards going back to the origin, then such a bound exists. But if the probability of going to the origin is 1/2, then the bound doesn't exist anymore. So it kind of depends on the exact values that occur in the program. So there's no easy, purely syntactic criterion. But we have a theorem that involves an additional condition of some martingale to exist. And then we could show that under certain other assumptions, something like this exists. So yeah, a bit more than syntactic.
Thanks.
Hi, thanks for the great talk. I have a question about the last curve that you show. You said you can have multiple upper bounds. And as a user, how do you choose which one to?
What objective you want to optimize for. So you can say, for example, I want to minimize the total mass of the bound, or I want to minimize the tail behavior. Like I want the tail to decay as quickly as possible, or I want to minimize the expected value of the bound. So the user can specify the optimization objective.
Right, but you have a finite set of choices that you program somehow in your system. And we need to choose about.
Yeah, so currently, yeah, we implemented a finite set of choices, but in principle, you could support anything that polynomially depends on the parameters of the EGDs again.
Cool. Thanks.
Thanks for the talk. You mentioned higher moments. Can you say a bit more the challenges involved in computing them? Because they're not linear, right? So I assume some of the tricks that you can use for probabilities do not quite work there.
So you said they're not linear? What do you say? I didn't quite hear.
So higher moments are not linear. So some of the nice tricks that you have for computing expected values and probabilities do not quite work there.
Right. So for geometric distribution, there's like closed form formulas for how to compute the higher moments. And we were able to adapt those to EGDs as well. So in the end, it turns out it's just some rational function in the parameters of the EGD. So it's possible to compute it. Yeah. And everything stays polynomial. So.
Thank you. Do you your semantics seems to consider only terminating programs? Can you extend to then some that do not terminate? For example, you would like to know my program never terminates, but the probability that x is greater than 10 is very small. This has a lot of application in the avionics industry where they must anticipate the probabilities of failures.
Right. So the second semantics, the geometric bound semantics, only works if the program is almost surely terminating. In fact, it has to be positively almost surely terminating. The other semantics you could apply, but you wouldn't get convergence of the bounds. So for the bounds to converge, you need your program to be almost surely terminating.
It should be possible.
Yes, your bounds won't be super tight, but it should be possible, yeah.
So next up, we have Rasmus Mølberg from IT University of Copenhagen, who's going to tell us more about probabilistic programming in guarded type theory.
Is this working? Microphone? Okay. The slides are not working. Okay. So probabilistic programming is everywhere, also here at POPL. And there are good reasons for that. It's because it's used in important applications like machine learning and statistical modeling, and also in security. Now, we'd like to be able not just to program probabilistic programs, but also reason about them. And that's particularly challenging when the programming language has other features, such as recursion and higher order functions. So let me start with a few toy examples of the kind of reasoning that we'd like to be able to do. And so here's the hesitant identity function. The hesitant identity function takes an x as input, and with probability p, it returns the x. probability 1 minus p, it calls itself recursively. Now this hesitant identity function, with probability 1, it will eventually return its input. So it should be contextually equivalent to the identity function, and indeed we prove that using the methods here in this paper. Here's another small example. It's an encoding of a fair coin using a bias coin. If you have a bias coin, you can encode a fair coin by flipping the bias coin twice. If you get different results, you pick the first result. If you get the same result, then you try again. So this is a recursive program here. And we prove in this paper also that, that this encoding is indeed an encoding of a fair coin. It's equivalent, contextually equivalent to a fair choice between true and false. In the paper, we also have some reasoning about Markov chains. Now, there has been a lot of work in this area. And indeed, all these examples that I show here, they have been proved in other settings, in other, using other tools. But the challenge here is that modeling this combination is quite challenging, and so the existing models are all quite complicated. And so what we'd like to do is we'd like to develop a simple model of this combination of features. And the way we do that is that we express this model in a powerful meta language. And the meta language you use is clock cubical type theory. It's a type theory that has guarded recursion in it. And we use guarded recursion for modeling recursion in the object language, for constructing relations between syntax and semantics, and for reasoning about programs. And in particular, we introduce the guarded convex delay monad as a way of modeling this combination of probabilistic choice and recursion. And so you may say that what we're doing is that we're delegating the difficulties in modeling particular recursion to the model of the meta language. So let's look a bit closer at what we do. So probabilistic computation by itself can be modeled using the finite distribution monad. And here I have the classical presentation of the finite distribution monad. And this would be used both for constructing operational and denotational semantics of these languages. Now, recursion is generally harder to model. It's usually not just a monad. Instead, the standard model of recursion is domain theory, and that requires a complete change of the setup. Or you could use step indexing, and that's also quite complicated. So it turns out that there is actually a monad for recursion. This is a delay monad, and it's a co-inductive solution to this type equation I have here. So it says that a computation in this delay monad is either a value of type A, or it's a computation that can run for at least one more step. And it's co-inductive, so you can be infinitely often on the right-hand side here, and that corresponds to divergence. And this monad is actually used to model recursion in type theory. It's also used in interaction trees. And we can easily combine, extend this to also model probabilistic choice in what I'll call the convex delay monad, which is the co-inductive solution to this equation down here. Okay, so this one says now that a computation now is not either a value or computation that can run for one more step, but a distribution of such things. And so this is actually a very natural model of this combination of recursion and probabilistic choice. So for instance, if we're modeling the geometric process here, which given an n returns n with probability p, probability 1 minus p calls itself recursively by n plus 1. We can model that in this monad as a tree like this, where the branching here is a distribution. And so the idea is that we want to represent terms of the programming language as these kind of trees, because once we have represented a closed term, at least, as a tree like this, then we can start doing basic operations on them. So for instance, we can run such a tree for one step, so eliminating one level of steps here like this. Or we can run it one step more, and it looks like this. Okay? And then after 2 steps, I can measure the probability of termination after 2 steps by just summing up the probabilities of the values, in this case 0, 1, and 2. Okay? And then I can define sort of a limit process, and the limit of this thing here is then the probability of termination of the whole process. Okay. So that's all good and nice, but there's one problem here with this convex delay monad, and it is that that it's not really a model of recursion, at least not for higher order languages. So it models an iteration operation of this type here, but there's no general fixed point operation of this type down here. Okay, and this is a problem when you're modeling higher order languages. And so this is the place where we step to a guarded recursion. So we replaced the convex delay monad that I showed you before with a guarded convex delay monad. And it's the same, it satisfies the same type equation as we saw before, except that the computations now are delayed by this modal operator later on clock kappa. Okay, so we're no longer just in ordinary set theory, in ordinary type theory. Now we're in a type theory that has guarded recursion. And it means that we have this modal operator, and we have an operation next which transports data into the future. So later X classifies data of type X, that's delayed by one time step. So next transports data into the future, and we have a fixed point operation like this, and a Carnot-style fixed point. And that fixed point operation is very powerful. As a small example, you can encode, for instance, diverging computation as an element of this monad here. And so the benefit of this monad here, the guarded convex delay monad, is that it does actually have a fixed point operation of this type here. So we can use it to model also higher order languages with this combination of recursion and probabilistic choice. And moreover, we can pass through the co-inductive monad, the ordinary delay monad that I showed you before, by simply quantifying over the clock kappa used in the definition of this guarded convex delay monad. Okay, and this gives us a way of having the best of both worlds, of the co-inductive and the guarded world. So in the paper, and a few more details, in the paper we work, as I said, in clock cubical type theory. It's a type theory with guarded recursion. One way to view this is through its free-sheaf semantics. And the free-sheaf semantics captures, in a way, the essence of the step index model. So you can think of this as an abstract language for step indexing. But you can also work directly with it in an extension of cubical acta, although we haven't used it for this particular application. So what we do in the paper is that we model a language called probabilistic FBC, construct operational and denotational models. We prove an adequacy theorem, and then we use that adequacy theorem to do examples of reasoning. So let me show you a few more details of this. Here's the probabilistic FBC. It's the simply typed lambda calculus extended with recursive types. You have the fold and unfold, and then probabilistic choice. And so we define an operational semantics. And the operational semantics is just given by an evaluation function that takes a term of type sigma and returns a value of type sigma. Of course, that computation uses recursion and it uses probabilistic choice, but we can model that using this monad here. And so, for instance, if we're to evaluate an application, well, you evaluate m to a value, which is necessarily a lambda. Then you evaluate n to another value, and then we substitute the value into the body of the lambda and keep evaluating. And of course, we can't define this by induction or recursion on terms. So what we do instead is we take a step, as you can see with the next here, and that takes us under later, and it means that we can define this evaluation function by guarded recursion using the fixed point operation I showed you before. We can then pass through the co-inductive evaluation by simply quantifying over the clock. And this means that we can define, for instance, contextual equivalence like this, essentially the standard way. So you take, you say m smaller than n in this relation here for any context. When I put these terms in the same context and I evaluate, then measure the probability of termination, then the probability of termination on the left-hand side is smaller than on the right-hand side. The denotational semantics is even simpler. So it's essentially Modge's corpora value semantics, monadic corpora value semantics, as we can see from the function space over there that uses the monad, the guarded convex delay monad. And then recursive types are modeled using guarded recursive types, which exist in this meta-language. So here, interpretation of terms for a function application is just monadic bind. We then construct a logical relation. In fact, we construct two logical relations, one between semantic values and syntactic values. another one between semantic terms and syntactic terms. And in fact, the second one of these is obtained from the first one by a lifting operation, which is one of the main technical contributions of the paper. So the lifting operation uses couplings, but I don't want to go into details of that. The value relation is defined also by guarded recursion. If, for example, in the case of the recursive type over here, we're going on that later, and that's how we define it by guarded recursion. And so we prove the main theorem here, which says that if the denotation of m is smaller than the evaluation of n in this relation here, then m and n are related in this contextual equivalence, contextual approximation relation. And so we can use this main theorem here to prove to reason about programs. And I'll just do a small example of this. Here's the hesitant identity function. Takes an x, returns x with probability p. Probability 1 minus p, it calls itself recursively. And we'd like to show that that's equivalent to the identity function. And I'll just sketch one way of this proof here. So in order to show that the hesitant identity is related to the identity, it suffices by the main theorem to show that the denotational semantics of the hesitant identity is related to the identity function. And because this is a logical relation, in order to prove that, we just need to show that they map related inputs to related outputs. So suppose we're given two related inputs, small v and capital V. We need to prove one here, which says that the results of applying these are also related. And so how do we do that? Well, we unfold the definition of the denotational semantics of the hesitant identity. And that unfolds the recursive definition of the hesitant identity and adds a step. And because it adds a step here, by definition, this one here would be equivalent to a relation of the unfolded things, but later. And that means that we can prove this one here by guarded recursion, okay? So by that I mean, to prove one, it suffices to prove one, assuming that later one holds. And if we assume later one holds, then we can prove two, because that's a statement under later. So if we assume later one holds, then two holds, and two was equivalent to one, and the proof is done. Okay, in conclusion, we saw that we could use clock cubicle type theory, which is a type theory for guarded recursion. We use that as a meta-language for doing semantics of probabilistic FPC. We used guarded recursion both in the definition of the operational and denotational semantics, and also in constructing this relation here. And I believe that this is perhaps the simplest possible construction you could do of this. What we're doing, as I said, essentially is we're delegating the difficulties in modeling recursion to the modeling of the meta-language. Okay, thank you.
Thank you, Rasmus. Any questions?
So you use guarded recursion to define the operational semantics. How much work would it be to show that that definition of the operational semantics is kind of equivalent to a more naive thing that's just defining it in terms of iteration and limiting the number of unrollings of the loops?
So we looked at various different definitions of operational semantics. I think there are different ways of constructing operational semantics for probabilistic languages. So I would expect it to be relatively straightforward to prove that for some of these, but we haven't done it.
And can I do that proof kind of internally in the type theory?
Yes, absolutely, yes, yeah. Well, we haven't done it, but I would be very surprised if you couldn't, yes.
I have not really understood what the type.
Sorry?
What is the guarantee that is provided by typeable expression relative to their semantics? I have not understood that.
The guarantee that what, sorry?
When you have a program which is typeable, the fact that
Yes.
But type system.
Well, we guarantee that the definition of the operational and denotation semantics is well defined. I think that's all.
But that's undecidable.
Well, I mean, so so what do type systems do? I mean, they guarantee that programs don't go wrong at runtime, you might say. Right? So that's.
And what does it mean, go wrong?
Well, it means they're applying something that's not a function to an input, for instance.
So for example, you have no probabilistic guarantees?
Not just from typing, no. I mean, so the idea is that you can write whatever language you like, and then you can reason about it afterwards, using these tools that I showed here. So you prove it afterwards.
Okay. I don't see the real progress, but maybe I'm the only one.
Questions? Right here.
Thanks for the talk. This might be a naive question, but is there semantics of the meta language? And if you sort of were to unfold going through like your encoding and then the semantics of the meta language, do you have a sense of how this relates to other approaches of giving semantics to FPC, probabilistic FPC?
So you would get a step index model, because the semantics is a pre-sheet model, which, as I said, encapsulates those step index models. Yes. So I think you could do that. Yeah.
Any final questions? All right, let's thank Rasmus then. Right, so...
how does this sound?
Good.
Sounds good.
We get the slides on as well?
Yeah, sure.
Oh. Great. So next up we have Julo Bao from Cornell University, who's going to talk about Bluebell.
Hi. Before you guys can go to lunch, I want to tell you about our paper, Bluebell, an alliance of relational lifting and independence for probabilistic programming, for probabilistic reasoning. My name is Jia Lu. I'm a PhD student at Cornell University, and this is a joint work with Emmanuel at University of Constance in Germany, and Azadeh at University of Toronto in Canada. Our work situates in the space of deductive verification of probabilistic programs. So the overall goal is to try to prove a probabilistic program satisfies some specification. And in this space, existing techniques can be roughly divided into two camps. The first camp is unary reasoning, where one proves property of a single program. And the second camp is relational reasoning, where you are concerned about how two programs compare to each other. So you would compare the two programs and their outputs. With Bluebell, we identify a small set of a small but expressive set of reasoning principles from which you can recover reasoning principles for both unary reasoning and relational reasoning. And because we provided a unifying foundation for both unary and the relational reasoning, in our framework, you can mix these two styles of reasoning together. And not only that, because we have both of them, we also identify some new reasoning principles that unlock new proof strategies. In this talk, I'll first overview some existing techniques in unary and relational reasoning space, and then try to advocate why we want to mix them together through a simple example. last, I want to touch a little bit about how we do that. So when you want to prove a unary goal, a current state of art or in technique in the community is probabilistic separation logic. Let's see how it works in action through a small example. So here, this is the program for one-time pad encryption. You have some message drawn from some distribution. Here, the message is a Boolean, and it can be drawn from any distribution over Booleans. And we want to encrypt that into a ciphered message C and ensure that knowing the ciphered message does not tell you anything about the original message M. And this specification can be expressed as the independence of the original message M and the ciphered message C. In terms of probabilistic separation logic, this condition could be expressed as this assertion. As in other variants of separation logic, there's a star, which is an additional conjunction added to the first order logic. And in probabilistic separation logic, the star is used for asserting probabilistic independence. So the reasoning of this program will proceed as the following. In the beginning, we start with a trivial precondition. After the first sampling, you know that M is distributed as such. You can do the same for the second sampling if you start from the trivial precondition. In probabilistic separation logic, there's the frame rule, which allows you to do reasoning more modularly, which says that if you can prove that starting from a precondition phi and run a program C, then you can always end up with a postcondition psi. Then suppose you instead start with a stronger precondition, saying that you not only have phi, but have some independent fact, alpha, and this C does not touch alpha. Then in the end, alpha is still valid, and is also still independent from the postcondition psi. And people often call this alpha the frame. And here we can treat the assertion M distributed as POPL'25 as the frame and put them here. And this gives us this assertion after the two assignments. And that is enough for guarantee that if we take an XOR of M and K, C is independent from M. If the last step sounds mysterious, don't worry, I'll come back to that later. But sometimes the goal that you are interested in may not be unary. Maybe the goal you are interested in is that two programs are equivalent. Then in the community, people have also developed techniques for reasoning about programs relationally. And there are a few talks on that as well, just at this conference. And the key idea is that you can reason about two programs in lockstep. Here I have two very simple programs. And in the following, I'll use angular brackets to denote the index of the program. So this is program 1, and this is program 2. In this case, assume that B is the same at the beginning of the programs for these two programs. Then we can reason in lockstep that after the first assignments to X, we have X at program 1 equal to 1 minus X, 1 minus X at program 2. And in the end, we have Y at 1 equal to Y at 2. This is nice. And then what if we have the program draw samples from distributions? In the previous case, we align the program execution perfectly in lockstep. But when the program makes samples, then there's not only a single program trace, there are multiple ones, and the samples from one of them probabilistically. A cute idea also from the community is called the coupling method, which says that we could correlate the execution of these two probabilistic programs so that to make it easy to pair together their program traces. And in this case, we can correlate them by flip a coin in the background, a fair coin, and assign its result to B. And instead of drawing sample links in program 1, we assign B to X. And similarly, instead of drawing sample at program 2, we assign 1 minus B to X. In this case, because B is drawn from a fair distribution, 1 minus B is also fair between 0 and 1. And if you only look at one of the programs, you will notice that we haven't changed the distribution, the output distribution of the program. But now we have paired together the possible traces of these two probabilistic programs, such that we can reason about them in lockstep. So we can proceed with a similar reasoning, which would show that we have paired together the program traces such that in each pair, in the end, we have y1 equal to y2. Notice that here, what I wrote are assertions for pairs of deterministic program states. But the whole sentence I just said that we can correlate the two programs such that we match their traces, and so that each of them satisfy these assertions. This is assertion on pairs of probabilistic distributions. In the literature, they denote this using, they call, we in this talk will denote this using the floor brackets. And in the literature, this kind of assertion is called relational lifting. The cool thing is that a lot of interesting properties about pairs of distributions can be encoded through this through relational lifting. For example, the distribution equality can be encoded as the relational lifting of just this equality. So in this case, from this relational lifting, we can infer the distributional equality of y1 and y2. So we've seen a little bit about both unary reasoning and relational reasoning, and they seem to be very different. It might be unclear why we want to mix them and how we mix them. And next, I'll show through a simple example that claims that we miss some opportunities if we do not have them together. So here are two other programs, which are also very simple. If you look at them, both of them draw samples and assign to x and y. And y in both programs are drawn from the same distribution. Similarly, x in the two programs are drawn from the same distribution. And x and y are independent at program 1, and x and y are independent at program 2. So intuitively, output distribution of program 1 and output distribution at program 2 should be the same. So one question is that, can we establish this relational lifting in lockstep? The problem is coupling method requires proving in lockstep. So here, if we align the two programs as before, then after the first line at the two programs, there's nothing interesting we can establish about the x at 1 and the y at 2, because they are drawn from different distributions, and it's hard to correlate them in an interesting way. We can align them differently. For example, align the two x together and construct and show that we have this relational lifting, from which we can infer that x at 1 and x at 2 have the same distribution. We can also align them in this way, which show that y at 1 and y at 2 have the same distribution. However, can we infer from the fact that we can prove both relational lifting, that we can combine them into one relational lifting? This is unsound. But in our intuitive reasoning, we use the fact that x and y are independent. So in this case, actually, if we can prove that we can use independent resources to construct a two relational lifting, then we can actually combine them together. And independence is inherently a unary property. It doesn't make sense to talk about independence between two variables in different programs. So this rule only makes sense if we mix unary style of reasoning and relational style of reasoning. So next I'll proceed in the unary reasoning side. I've first shown you some reasoning about independence. And there are follow-up works to extend that to also prove conditional independence. On the relational reasoning side, for probabilistic programs, people have used relational lifting. And our observations is that relational lifting looks awfully like conditioning. And we unify them into what we call the joint conditioning modality. For the unary case, now I will quickly go through how joint conditioning works for the unary case. Suppose we have some distribution that satisfies this assertion. So it says that x is a fair coin, and the fact that y and also y is always equal to 1 minus x. What if we condition on x? In this case, it's simple. If we condition on x, then with probability 0.5, then we have x equal to 0, and this fact holds because it always holds. And also with probability 0.5, we have x equal to 1, and this holds still. In terms of our conditioning modality, we can rewrite this formula as this thing. So the flip 0.5 here comes from the fact that we're constructing this distribution, and x equal to v is just an abbreviation because we want to combine these two branches. And this is the same. For the relational case, so first, I just copied over what I had from the last slide, but I added the index because now the variables are all referring to variables at program 1. And continue from our example in the coupling case, I would assume that at index 2, we have some distribution satisfy this assertion. Again, we can do a case analysis of the second distribution. So like, if we want to condition on x at that distribution. And one way, and the case analysis would say that with probability half, we have this assertion hold, and with probability half, this other assertion hold. And so what we want here in the relational case is to condition x1 and x2 together. I would say there are many ways to condition on them together, but one way that, okay. One way to condition them together is what we showed in our coupling proof that would relate x at 1 and x at 2 together. This joint conditioning modality satisfies a lot of useful and expressive rules with which we can derive all rules in probabilistic relational Hoare logic, and also new principles for derived relational liftings, such as the one I showed before. And this is another example. And also, unary reasoning becomes more powerful. Recall the example I showed in the beginning. In previous paper, they need to use ad hoc axioms about XOR to bridge this gap. But with rules for the joint conditioning, we no longer need those custom axioms. In the paper, we included more examples. And also, I want to comment that the research doesn't come in vacuum. In the community, there have been a long line of research in probabilistic relational logic. And the idea of using the coupling method and encoders in program logics comes from this POPL' 2009 paper. And the idea that that assert independence using separation star comes from this POPL' 2020 paper. And our joint conditioning modality was heavily inspired by POPL' 2023 paper, which introduced unary conditioning modality to encode conditional independence. So if you're interested in our paper, feel free to scan this QR code. And also, my collaborator, Emmanuel, is hiring students in Germany. Yeah.
Thank you, Julo. Any questions?
Thank you for the talk. It's very cool work. Can you go back to the slide where you show the relational version of the joint conditioning modality?
This one?
Yes.
Okay.
Can you explain how the binders rule work? Like the V is bound to the flip 0.5?
Oh, which one? Like this line?
That one. Sure, yeah.
How do I write? Am I writing this? Or?
I guess the question is, so on the top you have two flips.
Yeah.
But on the bottom you have just one flip that is bound to the variable V. Right, so is this...
could you ask your question again, sorry?
Yeah, how does the conditioning modality bind the V to the two flips?
So
that they are, I guess you want them to couple them, right? Is that the point?
Yeah. So in this case, so first let's start with the unary case. We bind V to this distribution. So V is sample from this distribution, and X is equal to V. And this is equivalent to like condition on X. Like the assertion you make here are true if you on the distribution condition on X. And in this case, V is sampled from this distribution, but we can assert things like both between V and variables at program 1, and also between V and program and variables at program 2.
So okay, thanks. So if you had, I mean, normally when you have a coupling, you compute some kind of joint distribution and you sample from this distribution.
Yeah.
So could you do this in your setting instead of just?
Yeah. So here this is one way to rewrite these tuples of assertions. There are other ways to rewrite them, and another way is say that we put another distribution here, which is like you flip two independent coins, and both of them are fair, and then you'll get two variables VW, and you can use VWs at different places in the assertion here.
Okay, thank you. I think I got it.
Okay.
Yeah.
One final question for lunch.
There's a question.
So do I understand right that if I want to prove a relational property using this, it's not that there's like a specific relational judgment, it's that I have to sort of show that conditioning on a bunch of background variables that I'm introducing, the statement just holds? Or how do I actually get my sort of relational property proven?
Yeah, so if you can do the proof in traditional like probabilistic relational Hoare logic, because we derived all their rules as well, you can just do all the proofs in that style. But we provided, so in our logic, we define this relational lifting through conditioning modality. So it provides you other ways to establish that relational lifting. Does that answer your question? Okay. Okay.
I think we're out of time.
Okay.
Thank Julio again.
Thank you.
So this concludes this session. Thank you so much for coming.
Okay, welcome to the afternoon session. We have 3 papers in this session. And the first one is about the decision problem for regular first order theories. And the talk is given by Uma.
Welcome, everybody. I'm Umang Mathur, and I'm an assistant professor at NUS. And this is joint work with David Mestel, who is also an assistant professor at Maastricht University, and my former advisor, Mahesh Vishwanathan at Illinois. So for some of you, the title may sort of appear very complicated, and a large part of the talk will try to disentangle the complications in the title. And subsequently, I'll talk about the results of the paper and how they matter for PL research. Okay, so let's focus on the first part of the title, decision problem. If you have not taken any formal logic course, the decision problem asks, given a first order formula or a formula in any kind of logic, tell me whether that formula is valid. So this problem has been sort of the cornerstone of foundations of both mathematics and computer science. In fact, Hilbert, in his list of many, many problems, the 10th problem, which is also one of the most famous problems, asks if you can basically come up with a finite axiomatization for the set of all valid statements in mathematics. And to be able to have such a mechanization, such a mechanical procedure, you basically need to solve this decision problem. Okay, so this was the decision problem, which was about a single formula. In this work, we try to generalize this concept, and we look at a more general question, which is, this time, you're given a set of formulae, which we can call a theory, and now you're asking whether this theory is valid. Now, of course, because so T can be possibly infinite, and the concept of validity of a set of formulae is not clear. So in fact, you can have 2 different interpretations for this. The first interpretation is that there is a formula in this theory that is valid, and the other interpretation can be that every formula in this theory is valid, right? So these are exactly the 2 questions that we study in this paper. A mild modification of the same question gives you this problem statement. It says you have a theory T, which is basically a set of formulae. Think of these as formulae on first order logic. And the question that you ask is it the case that there is a common structure, first order structure, that satisfies all the formulae in this theory at the same time, simultaneously? The other variant is the following. It says, is there a formula that is satisfiable in this theory? Right? If T was singleton, meaning a single formula, the 2 questions sort of are duals of each other, but not here. You sort of, an algorithm for the first question doesn't give you an algorithm for the second one. That's why there are 2 different variants. Okay, so that was the first part, the decision problem. Let me try to also detangle for you the second part of the title, which is about regular theories. So what is the regular part? The set T itself is what I'm talking about. To be able to understand what I'm saying, you need to understand that a formula is essentially a tree. Right? So over here, this formula says that the variable y is not equal to f of x. And likewise, this is a bigger formula, which I don't think I want to read out. But it's a conjunction of 2 subformulae, each of which have existential quantifiers. Okay, so now that you understand that a formula is essentially a tree, a set of formulas is a tree language. And you can talk about different kinds of tree languages. A very popular class of languages is tree regular languages, which is essentially those languages which can be represented using a tree automaton. That is, there's a tree automaton that accepts exactly those formulae or trees that are in your language. Right? So here I've not represented them as tree automaton explicitly, but even if you express these trees as context-free grammars, that's really an identical representation because parsed trees of context-free languages are essentially tree regular languages. So over here, the first language is the set of all formulae of the kind y is not equal to f raised to nx, where n can be any number from 0 to infinity. Likewise, the second formula is essentially a representation of something more complicated. It says that either y is not equal to x, that's one string, that's one formula, or the other formula is that, well, what does it say? So it says there is an x prime which is equal to f of x. So, and now inside that I'm re-quantifying x, and I'm saying that the new x is the older x prime, which is actually f of the older x. And then the remaining thing can be sort of recursively computed. So these languages are essentially tree regular languages. All right, so having understood the different parts, let's put them all together. The problem statement says you first fix a first order signature sigma, and you ask that, and now you're given a theory T over this signature. Now your question is it the case that there's a common model that makes every formula in this set satisfiable? And likewise, is there a formula in this set which is satisfiable? Okay, so why are we interested in this really obscure question? I just want to emphasize that this is not an obscure question. In fact, if you think about program verification from the perspective of algorithms, and if you let go of the syntax-driven style of proofs as in program logics or whole logic, the slightly different approach here would be to look at executions of a program and try to establish that each of these executions are correct. How does this go? So if I have a program here, and if I want to check whether it satisfies the following post condition, assuming the precondition is true, I can essentially put back the post condition as an assumption with the negation at the end of the program, and then ask whether any of the executions of this modified program are feasible. Right? So from program verification, I could translate it into a problem about executions or set of executions. Observe that, at least for here, this set of executions is also a regular language, a regular word language. I can go one step further, and I can actually translate this problem into a regular first order theory. So over here, I give you the context-free grammar for the same language. Observe that the set of formulae that this execution generates is essentially what you would get by performing a symbolic execution on each of these executions. Okay? So every execution corresponds to a constraint, and checking whether that particular execution is satisfiable or feasible is the same as asking if the corresponding formula is satisfiable. So bottom line, if you have the task of verifying a program, you can pretty systematically, mechanically compile it down to this problem of checking whether a theory is satisfiable. Okay? So that's a very natural motivation to look at this problem. And of course, this concept of coming up with the set of behaviors as a language and then translating them as formula doesn't really just is not limited to program verification. You can also apply the same concept to program synthesis. This time, your set of concepts is a set of programs coming from a grammar, and you'd like to see if there is a program in this grammar which satisfies the specification. This time, each program itself, you can think of it as a formula, maybe on a very different logic, or if the grammar ensures that there are no loops, then pretty much in first order logic. And now the question again becomes a similar question about disjunctive satisfiability of a regular theory. Recent works have shown that, in fact, similar problems can be solved, problems around learning formulae from concepts can also be essentially translated into something very similar. So bottom line, even though this problem may look very unnatural, it actually is the most natural version that I can think of. Okay, so where do we stand? In this paper, okay, since I just have 5 minutes, in this paper, we're essentially looking at the computational aspect of this question. Meaning, given a theory, tell me whether that theory is satisfiable either conjunctively or disjunctively. Observe that even in the degenerate case where the theory is singleton, this is an undecidable problem. So the more natural question is, are there fragments of logic for which, if I give you a theory on that fragment, is the problem decidable? Okay, so this style of questions about what fragment of logic is decidable is not a new question. In fact, people in communities like LIX regularly ask that question. Okay? And one popular way of phrasing this question is to come up with syntactic fragments. For example, over here, this is the fragment of logic that contains all the formula whose pre-index normal form has quantified prefix exists cube for all exists star, and it has 3 relation symbols of arity 1 and 7 relation symbols of arity 7, and likewise the next thing tells you about the function symbols and their arities. Popular decidable classes for the usual decision problem are essentially encodable in this format. So the EPR fragment would be something like exist star for all star. You're allowed all relations, but you're not allowed any function symbol. Okay, so what did we find out? The very popular EPR class, which enjoys a lot of applications in program verification, quickly becomes undecidable when you ask the question in the context of regular theories. Okay, so these are both fragments of EPR, and they become undecidable. And that's because the canonical small model property doesn't really generalize to regular theories. So we had to sort of make that property much more specific, and we call it the bounded model property. We come up with 2 different variants of it, and we show that when you have any of these properties, you can actually show decidability, but for the more general question. In the interest of time, I'd not like to sort of go about the other ones. The 3 boxes with the syntactic fragments essentially make use of some version of bounded model properties. Okay, how much time? Sorry? Okay, so I do have some time. So if there are more questions and I don't have enough time, I'll ask you to just come back to me after the talk and we can take questions later on. So EPR, which is famously known to be decidable, quickly becomes undecidable because you can encode the post-correspondence problem here. This formula says that, so this formula only uses, this set of formulae only uses 2 predicates, S0 and S1, which are both binary. The S0 means the 0 successor, and S1 means the 1 successor. So you're essentially trying to construct these 2 strings and walk through them. And at the end, you'd like to check if the 2 strings that I constructed are equal. And that you can do pretty easily when you have EPR and sets of theories and sets of formulae. So coming back to small model property, which was the heart and soul of EPR decidability, the decidability really comes because of this small model property, which says that if you're talking about a fragment F, and if I give you a formula in that fragment, then checking whether that formula is satisfiable boils down to basically analyzing a bunch of models whose size is, upper bounded by some constant. Now the nuance here is that that bound may be dependent on the size of the formula. Okay? In particular, for example, if you look at the EPR class, that bound is really the number of existential quantifiers that you have in your formula. Right? Now this doesn't gel well when you have an infinite set of formulae. So that's why we have to strengthen this condition. So the condition is pretty natural. You fix the constant a priori. Okay? Don't let it depend on your formula. And then you say your fragment is said to have this nicer property, bounded model property, if no matter what formula you take, independent of its size, the models that it can be true on, or the model that can witness its satisfiability, are bounded by that constant, which is independent of the size of the formula itself. Moreover, if this constant is also computable just based on the signature, that's even better. And that's the property of strong bounded model property. So where does this come? As in, where does this help? If you have a fragment which has this property, then the conjunctive satisfiability problem becomes decidable. And when you, on top of it, also have the strong model property, both these problems become decidable. Right? So what is the basis of this theorem? Before that, the two fragments that I mentioned in the beginning are really an outcome of these two meta-theorems. So what is the proof of why you get decidability when you have bounded model property? Essentially, the idea is that if I fix a model, then I can construct a tree-regular set of all the formulae that would evaluate to true on that particular model. Of course, the size of the presentation of this tree-regular set may depend on the size of the model, but if you fix the model, it's really a constant size automaton. And that gives you this intermediate property that if I take any theory, then I can, in a decidable manner, determine whether that model is going to be a common model for everything or a model for something in the language. All right. Now let's sort of quickly take a slightly now let's jump to the other decidability result that we have in the paper. It's about a semantic fragment this time. It's no longer a syntactic fragment. And the idea is to not restrict the quantifiers, but instead look at how the formula computes terms as you walk across the formula. And this is a good example because this is an example of what can go wrong. Over here, if you have a formula, you can essentially try to annotate that formula with what is the term corresponding to each variable at that particular node. And when you do that, you would like that this annotation is consistent across all the paths in your tree. But that may not always be the case if your formula is not a nice one. In particular, over here, over this path, there is a term that is being computed, namely f cube x 0. But as you walk through the path on the other end, in the middle somewhere, that term gets forgotten. There's no particular variable that stores it. So that's the recipe for disaster. You would not get decidability like this. But when you do not have these kinds of problems, you essentially get a very automata-theoretic decidability result. I will not go into the details, but the point is, such formulae are called coherent formulae when they do not have these bad paths. And you can also check whether a formula is of this kind in a very automata-theoretic manner. And that gives you the other decidability result, which is the more semantic one. So where are we? Well, I basically represented to you another connection between logic and automata and how it is applicable to many different applications in program verification, synthesis, and a lot more things in computer science. And where do we go from here? Well, the bare minimum question that we should try to address is there a more thorough classification of the fragments and whether we can actually translate these results into the applications of interest. So that's all. Thank you so much.
Okay, so unfortunately, there is no time for questions. So please switch to the next talk. So the next talk is about primordial perspective on program verification algorithms. And this received a Distinguished Paper Award, so please congratulate. And given by Odette.
Is this on? All right. But the slides are not showing. Let's see why. All right. So thank you all for coming. And I want to talk about, like the title says, a primal dual perspective. And what I want you to think about is this sort of primal dual interaction that is very common in verification algorithms between proofs and counterexamples, where you have some sort of procedure that automatically searches for a proof and a counterexample. And those two searches are not just in parallel, they also guide each other. And you can even say that it happens when, when a human thinks of finding a bug in a program or proving a theorem, we kind of simultaneously think of proofs and counterexamples, and those two searches guide each other. And there are some nice examples of verification or automated reasoning algorithms where this occurs, but this is sort of informal. And of course, the classic example of this in computer science is linear programming duality and duality from linear optimization. And there are a couple of recent papers from POPL'22 and POPL'23 that had primal dual algorithms which had a more formal explicit duality. And those kind of motivated and inspired this work where we're trying to ask, is there a way to capture formally this primal dual interaction that is common in many verification algorithms? And hopefully this new insight can lead to new insight, this new perspective can lead to new insight on existing algorithms and also maybe to some ideas on designing new algorithms. And indeed, what we were able to come up with is a Lagrangian-based framework, and I'll explain what that is on the next slide, where it is inspired by linear programming duality, and it is able to capture many common algorithms from verification and automated reasoning. And it kind of reveals some interesting comparisons between existing algorithms. And another contribution that we have in the paper is a new algorithm for solving quantified fixed point logic whose design was assisted by this framework. But in the talk, I'm mostly going to focus on the new framework and the perspective that it offers. All right, so we take some inspiration from linear programming and linear optimization, where it's very typical to define what's known as a Lagrangian, which is a function from two sets to R. And it's common to define these two problems, I think the primal optimization problem and the dual optimization problem, where you see x and lambda here, and x is trying to minimize the Lagrangian, and lambda is trying to maximize it. And in the linear programming setting, it doesn't matter which order you take the inf sup or sup inf, and that's what's known as strong duality. Now, to apply these ideas to program verification, we generalize from the setting of just Rn, and we let x and y be general sets, and z be a totally ordered complete lattice. And in this case, it may not hold. Strong duality may not hold. This equality might not hold. But weak duality, which is an inequality here, always holds. And this is a very classic result. It's also known as the minimax theorem, and you can easily convince yourselves of that. All right, so this is pretty abstract. Now let's see how we're going to apply it to program verification. The setting that we're going to define is usually where X is the space of possible and maybe partial counterexamples, and Y is going to be the space of proofs. And we're going to define our Lagrangian to be, let's say, -1. So a Lagrangian of a certain X and a certain Y, a certain counterexample and a certain proof is going to be -1 if the counterexample shows that the proof isn't valid. And it's going to be 1 otherwise. And then we're going to derive sort of a two-player game from this Lagrangian, where the X player tries to minimize the Lagrangian by finding a counterexample that rules out the existing proof. And then the Y player tries to maximize the Lagrangian by trying to find a proof that rules out the existing counterexample. So this kind of leads to a pretty straightforward procedure that I'll present with an example. So let's say that this is our Lagrangian. And so we're going to start at some arbitrary point. Let's say we start at this point over here. And then we're going to enter into a loop. And at every step, we're going to let both players take turns. So the X player in this case is going to ask, can we change the value of X to make the Lagrangian negative? And if the answer is no, we're going to declare that the Y player wins and return the current value of Y. But in this case, of course, we can move here. So we're going to update X to a place where the Lagrangian is negative. And now we're going to let the Y player take a turn and ask, can we change Y to make the Lagrangian positive? If not, the X player wins and we return the current value of X. But in our case, we're going to update Y and to a place where the Lagrangian is positive here. And we're going to let this continue again and again. So the X player could move from here to here. And now the Y player can move to here. But in this case, the X player cannot make the Lagrangian negative. So the Y player wins, and we return. So this was a very simple example. But what happens if the Lagrangian looks a little different? Let's say it looks like this. So now we might start over here, and then go here, and then go here, and then go here. And now the Y player can take us back here. And we're just going to enter into this kind of live log situation where we continuously circle these 4 points, but we're not exploring any new area of the search space for proofs or counterexamples. So how do you get around this? The way to get around this, and this is what verification algorithms typically do, is that they use monotonicity. So if X and Y, which before were just arbitrary sets, if they have a lattice structure, and it's enough that one of them has a lattice structure such that the Lagrangian is either monotone on Y or anti-monotone on X, so X is trying to decrease the Lagrangian and Y is trying to increase it, then we can ensure progress. And the idea is very simple. We just take the same algorithm from before, and we replace this update by monotonic update. So where we, for example, take the join of the current solution with the new value that shows why the other player doesn't win. And for this modified algorithm, we can prove its partial correctness, its progress under the assumption of monotonicity. And this also can give us termination by stratification, where this is also a common idea, where if you systematically explore either proofs or counterexamples in some order, then you can guarantee termination in case a counterexample or a proof exists. All right. So now the real beauty of this simple algorithm is that we can now start to instantiate it with different Lagrangians and see that we get different existing algorithms from automated reasoning and program verification. So the first example we're going to look at is counterexample guided abstraction refinement, or CGAR. And the idea here is that we have a transition system and we want to prove safety. But the transition system might be very large or maybe infinite state space. And we're going to have some finite set of predicates. And we're going to use it to partition the state space of the transition system into a finite set of equivalence classes according to the valuations on these predicates. And then this is going to induce an abstract transition system, which is finite and possibly small. And we're going to check safety of that transition system. If that's safe, then we can terminate and deduce that the original transition system is safe. And otherwise, we're going to refine our abstraction. So the way this looks like is we might come up with we might discover an abstract counterexample where we start at an initial state and we make a transition, and then we make another transition, but not exactly from the same state, but from another state that is just equivalent up to this abstraction. And we continue this process all the way to a bad state. And then if we discover this, we just refine our abstraction by adding a new predicate that would break the equivalence between some of these states. So how are we going to get this algorithm as an instance of our Lagrangian-based framework? We're going to let X be sequences of states, and Y be finite sets of predicates ordered by inclusion. And then we're going to define our Lagrangian to be, so the Lagrangian takes a sequence of states and a set of predicates, and it's going to be -1 if this sequence of states is an abstract counterexample to the abstraction given by this finite set, and 1 otherwise. So now let's try to see what this game would look like. Let's say that we start with some set of predicates, and we let the X player play to minimize the Lagrangian. So what it's going to do, it's going to find an abstract counterexample like this. And now we're going to let the Y player play. So the Y player wants to make the Lagrangian Y. It's going to add to A, because we're going to update A monotonically. It's going to add to A some predicate that would make this condition false, such that it's no longer a valid abstract counterexample for this abstraction. All right. So now let's look at another example, ice learning. So in ice learning, it's also in the setting of safety verification of a transition system. The basic procedure is that we have some finite set of states which are positive, some finite set of states which are negative, and there are going to be initial and bad states, and some finite set of transitions. And we're going to try to find a predicate that is inductive, but just for these constraints, for this finite set of constraints. Let's say we find this predicate. And then we're going to ask ourselves, is this predicate a good inductive invariant for the whole system? And if it is, we are done. And if not, we might refine our finite subset of the transition system by adding a new transition. All right, so this is ice learning. And let's see how we can obtain that with a Lagrangian. So now we're going to let X be the cross product of 3 finite sets of states, transitions, and initial state transitions and bad states, ordered by the generalization of a subset here. And Y is just going to be our set of predicates. And we're going to define the Lagrangian as follows. Given some sets S plus, S arrow, and S minus, it's going to be 1 if P is a valid inductive invariant for these constraints, and -1 otherwise. So now let's see what this 2-player game looks like, right? Let's say we're going to start from some sets of states and initial bed and transitions. So now the Y player plays, and as they maximize the Lagrangian, they're going to find a predicate that is an inductive invariant for this. And now we let the X player play, and the X player, if possible, is going to add a new, let's say, transition to here that shows why this predicate is not a valid inductive invariant. All right, how are we doing on time? All right. So one interesting comparison that these kinds of lets us draw, it both kind of shows the common structure of these algorithms, and it lets us ask what side do they make progress on. And we see that CIGAR makes progress by accumulating predicate on the side of proofs, and ice learning makes progress by accumulating counterexamples on the side, on the side of counterexamples. And I won't have time to go into the details of other examples, but in the paper, we have several more interesting examples of algorithms which we are able to derive from this Lagrangian-based framework. And I will note some interesting properties of them. So for primal dual Houdini, it's a recent algorithm that is explicitly primal dual. And what's interesting there is that it makes progress in a symmetric way on both sides, both on proofs and counterexamples. And also the properties that we have that we derive from the Lagrangian framework, like progress, their proofs are pretty non-trivial for primal dual Houdini. But when you formalize it in the Lagrangian framework, what that translates into is that proving that the Lagrangian is well-defined somehow becomes non-trivial and has to capture the essence of that proof. So there's something interesting going on there, and I encourage you to see the paper for more details. A couple of more things I want to mention here. So we don't have to, this doesn't only apply to safety proofs, it also applies to algorithms for termination. And for termination, we kind of see that classic ideas like disjunctive rankings that let you kind of make use of multiple ranking functions can be seen as a way to make progress on the side of proofs for termination verification. Another interesting observation is that the algorithm for solving quantified formulas by strategy skeleton kind of reveals that strategy skeletons are a way to make progress for kind of quantified instantiation in the case of quantified logic. And the last row here is a new algorithm that we derive in this paper, and it kind of, using this perspective, it kind of combines strategy skeletons and disjunctive rankings to get an algorithm for validity of a combination of fixed point logic and quantifiers. So you can imagine how the disjunctive rankings are related to the fixed point logic, and the strategy skeletons are related to the handling of quantifiers. All right, another point that I want to highlight that is kind of a part of this perspective is weak duality versus strong duality. So remember that we have a space of possible counterexamples and proofs, and in general, our Lagrangian says whether the proof or the counterexamples wins. When should we expect strong duality to hold? Well, the answer is that it's going to hold if there is either a valid proof or a valid counterexamples, or a valid counterexample. And this would hold in finite state cases or in idealized versions. Maybe let's ask the opposite question. When would it not hold? It might not hold if, let's say, the system is safe, but our language of invariance is not expressive enough to express a safety invariant. Or the system is terminating, but our language for expressing ranking functions is not expressive enough for the right ranking. And this is, you consider this is kind of analogous to relative completeness from Hoare logics. All right, so let me conclude. Our main contribution is this general framework based on Lagrangians that captures many existing algorithms and kind of sheds new light on those existing algorithms, and it can also lead to new algorithms. There are many more details in the paper. I want to highlight a couple. One is this new formulation of primal dual Houdini, and the other is this new algorithm that we designed based on these insights. And really what I want you to take away from this talk is a call for action, right? I want you to look at this and take your algorithm or the algorithm that you're working on and ask yourselves, can it be formalized using a Lagrangian as we've discussed? And there can be two answers here. Both are great, right? If yes, that's wonderful. You maybe get some new insight and relate your algorithm to existing algorithms. And if no, maybe that's even better, because if you think that your algorithm has this primal dual interaction, but it doesn't fit this framework, maybe there is an extension of this framework that is waiting to be discovered. So that's all I had. Thank you, and I'm happy to take questions.
Thank you. Hi, great talk. Tom Ball at Microsoft Research. So if I'm doing abstract interpretation and narrowing and widening, and how does that intersect? Like, what can I tell? Can you give me some hints about, like, because, yeah, that's the question.
That's a great question. So I think we are also asking ourselves that, and I don't have a very good answer. I think you had the right intuition. It's the same that we have, that somehow that's the standard fixed point computation of abstract interpretation. That is not a primal dual, but where the primal dual interaction might come in is exactly in the widening and narrowing. And yeah, I guess answer is welcomed.
This was a very beautiful spin on the duality, and congratulations. So my question was regarding the convexity of the Lagrangian. So I think you've primarily worked on the convex setting. What happens if the Lagrangian is non-convex? Will you still be able to find either a counterexample or a proof?
So that's a very interesting question. I guess convexity plays a big role when the Lagrangian is over real vector spaces. For our Lagrangians, which are kind of over sets of predicates or sets of states, we haven't really defined the notion of convexity. And it would be very interesting to see what might be an analog of convexity in this setting. Yeah, I think it's a great question.
Yeah.
Thank you.
Thank you.
Yeah, yeah, okay, excellent. Slides are not on though. Can we get the slides on? Or? All right, excellent. Well, hello everyone, thank you for coming. So I'm George, as introduced, and this is a joint work with Pascal, Yarim, and Guido, who are somewhere around here, from the University of St. Gallen in Switzerland. And this presentation about our work on disequality graphs that kind of extend this magical data structure called the E-graph that's kind of very efficiently stores equalities and is able to reason about congruence. So E-graphs are these fundamental data structures that you will inevitably see inside provers or solvers. And essentially, they comprise of two operations. So the first one is adding equalities. For example, f of a GB is equal to c. And you can also find the equivalence class of terms. So for example, if I query for the equivalence class of c, I will get the equivalence class of f of a GB. And this is how I can tell that two things are equal. Right, so an E-graph is a graph. And so it has vertices and edges. And there are two kinds of vertices. The first one are E-classes, supposed to represent equivalence classes. I represent them with a circular here. And we can add things inside them. So here I add A, which is called an E-node, a term, an atom, inside of this equivalence class. This is yet another equivalence class that contains the atom B. So I can add things like that to my E-graph. So this is the application of f of A added to the E-graph, except this is not actually how we do it, because we know about A. So the E-graph knows about A, so instead it just represents it like this. So this edge, if you think a little bit about it, this is the thing that guarantees congruence. So this term now represents f of A and anything which is equal to A, f of anything which is equal to A. So to make this example a little bit more interesting, let me just add f of B as well. And this is how then we would equate two things inside of an E-graph, because now I just added things. If I want to say that A is equal to B, I just kind of merge their E-classes together. I fix the arrows, and I'm not actually done. Because if I scrutinize a little bit, these highlighted nodes, they represent exactly the same thing. They both represent f of A and f of B, so they ought to be equal. So their E-classes ought to be the same. So now I have to their equivalence classes. And I end up with this E-graph. So this example, I will go back to it multiple times in my presentation later on. So this, now that we are all experts on E-graph, I want to present to you my first contribution, which is a formal framework to reason about E-graphs. And the objectives of this framework is to be abstract and extensible. So abstract in the sense that it ought to kind of cover as many implementations as we are aware of, and extensible so that we can define extensions, which I will talk about a little later in the talk, so that kind of proving correctness theorems, proving bounds on these things is easy. And the other contribution which we did is that we present a novel correctness algorithm for these E-graphs that isn't just one giant proof, but we rather refer to a lattice. I will come to this in a little moment. So if you, in the next few slides, there will be definitions, theorems. You don't have to read them. I will guide you through them. If you don't like to see the stuff, you can go on your socials, tweet about the talk, and you can come back in a few minutes. So the way we define, for example, an E-graph is it's a triple of classes and nodes. One of the choices we did is that, for example, classes don't need to be different than nodes. This would cover some implementations that don't actually talk about classes, but rather use some canonical e-node to represent the class. Another kind of feature we have is in this complicated rule, which talks about how to merge two things, which kind of is this thing here when we want to equate two classes. But this is the thing I want to focus on, and here we are constructing the reflexive symmetric transitive closure. A lot of implementations kind of reduce this to using a union-find data structure, which essentially does this. So this would justify why these implementations are correct. And the last feature I want to show you is, again, how we did this correctness proof. What we did is that we kind of showed that the E-graph is correct, that it generates the smallest reflexive, symmetric, transitive, and congruent closure of some set of equalities by essentially referring to the lattice of equivalences. In 3.14, in theorem 3.14, we show that the smallest one in the lattice implies the relation that you get from the E-graph. In 3.15, we show the opposite, and they are equal as a corollary. This was pretty helpful for us because when we did the extensions later on, all the effort had to go in theorem 3.15. So we had a much kind of stronger theorem to work with, which made things easier. Okay, those on the socials, you can come back. Now I want to tell you a bit about disequalities. I think they don't get the appreciation they should get, and they are not covered often. And I don't have a slide for this, but if we go back to the first presentation in this session had a lot of disequalities in it as a motivation, but actual motivations also include SMT solvers. So here I have this formula, n is equal to m, and ffn is not equal to ffm. And I want to give it to an SMT solver to find assignments for n, m, and f if they exist. So how does this happen? The SMT solver converts it to a Boolean formula, p and not q, and it stores the aliasing that p is an equality between n and m, q is an equality between ffn and ffm. It queries the SAT solver for a model. In this case, yes, it's satisfiable. This is the model. And it feeds it into the E-graph. And now the E-graph has to use the knowledge that this equality is false to somehow figure out that there is a contradiction. So it has to be able to reason about disequalities. The other motivation comes from our project. It's called POPL'. It's an automated inductive theorem prover. We presented it at PLDI last year. And POPL' has a lot of properties. One of them is reasoning about disequalities. And when we wanted to explore the effect of reasoning about disequalities on the quality of proofs, what we did is we did a little experiment. We took the theorem that addition is commutative. We took two versions of POPL', one where disequality is enabled, one where it's disabled, and we tried to prove the theorem this way. What we got is essentially this thing. So this thing is a graph of all the states that the prover was in and all of the transitions it went into. At the surface, this looks like disequalities are horrible. They go kind of all over the place. There's a lot of things to go. But the caveat is that they both ran in the same amount of time. So kind of disequalities helped pruning a lot of these branches, and we went to discover many more states that we wouldn't if we didn't have disequalities. And with that, hopefully I convinced you disequalities are useful. And now I want to show you 3 ways how to do that inside of E-graphs. The first one is actually 2 versions inside of the paper, and they fall under the umbrella of what I call valued embeddings. And in here, the observation is that equality is a binary Boolean function, right? And an E-graph is meant to represent functions, so why don't we let the E-graph know about this function? I'll go back to my example from the beginning, and I'll show you how this works from here. So if I want to say that A is equal to B, I will not merge as before. Instead, I will just add these 2 terms, saying that the equality of the respective classes is true. If I want to say they are false, FFA and FFB are false, I would do the same, except I equate it with false. Now what I would do is I would need to also reflect the axioms of equality inside of this graph. For example, symmetry. I would need to duplicate every equality and kind of switch things around. I don't do this in the presentation. It just makes this very complicated. So trust me that there's this stage at this point. But now, how do we find out that there is a contradiction? What we would do is then first we would look at this pair. We know that this equality is true, so the graph ought to reflect this by merging the two E-classes. So now what it knows is also true inside. But we're not done, because after doing this, we look at this equality. This equality says that the same equivalence class is equal to itself. And of course, by reflexivity, this has to be true, which means the two classes at the bottom have to be merged together. And after doing that, this is the graph we get. If we focus on this part, this means true is equal to false. And so this is how we would find if there's a contradiction. The second approach is I call unvalued embedding. And here we are still embedding, except we're not giving values, because the main observation is that this equality is just a proposition, and the mere existence of some of these terms is a witness for the disequality. I'll elaborate a bit more. So going back to the same example, now when I want to say that FFA is not equal to FFB, I just add this term. In the valued embedding earlier, I assigned this a value. I said whether this is true or false. Now I just add it like this. If I want to say that A is equal to B, now I just do as classically is done in eGraph, and you merge the two equivalence classes. And the contradiction can be found by kind of looking at this pattern. This pattern is saying that an equivalence class is not equal to itself, obviously a contradiction. And the third approach is structural, and in many ways, the third approach is the first one historically. So this is a quote from Nelson in his PhD thesis from 1980, and this is the PhD thesis that introduced eGraphs. He writes, given a disequality, we must add structure to the graph so that if the nodes ever become equivalent, the program will detect it. The obvious way to do this is to store with the root of each equivalence class a circular list of nodes that are forbidden to join the class. Elaborating a bit more on it, go back to my example. If I want to say that FFA is not equal to FFB, now all I need to do is add this edge. This dashed edge between E classes represents the fact that they should not merge, or that they should not be equal. Now when I equate A and B to create a contradiction, this becomes a self loop. And in fact, it is this pattern, this self loop, which is the indicator that there is a contradiction. Okay, so I've shown you these three approaches, 4 in the paper. Why did I do this when the last one was like 40, 45 years old now, published and all of that? It's because when we looked in applications to see what is actually used inside of SMT solvers, and we looked at these SMT solvers, we did not find the published technique, which is the Nelson one, except in OpenSMT2. So OpenSMT2's eGraph is exactly as Nelson describes in his PhD thesis. Z3, on the other hand, embeds both disequality and equality, but without giving them a value. So this is why it's a little bit off from the unvalued, because it also embeds equality. CVC5 also embeds both, except it gives them a value, but without needing to reflect all of the axioms, and kind of refers back to the unvalued embeddings way of finding a contradiction. So what gives? Which is better? And so this is kind of what we wanted to do. So the first thing we did was we used our nice extensible framework, which I talked about a bit earlier. We extended it to talk about the 4 variants. And we proved they're correct, and we proved some bounds on them. I will not show you the theorems about the bounds, because the results are kind of the same as the case studies. So we have some case studies, and it's exactly the same. So I will only show you that. So the first case study we did is that we took our inductive theorem prover, POPL', and we made it use these 4 eGraphs, and we kind of measured the resources it took. So the first resource is time, and this graph, what you see is on the x-axis, the time, and on the y-axis is how many benchmarks it could solve given some time. So what you should be on the lookout for are very steep, kind of fast-growing lines, because these are the lines corresponding to the approach that is better. And in this case, the structural one, so the one with disequality edges, performed better time-wise than the unvalued embedding than the valued embedding. And we didn't only measure time, we also measured memory, but by proxy of counting the numbers of classes and nodes inside of the E-graph. And what we saw is exactly the same for the application of inductive theorem provers. The next case study we did is that we implemented the core of an SMT solver, which is, or a kind of part of the SMT solver, which is the equality and uninterpreted function part of the SMT solver. And it uses internally a mini-SAT and an implementation of the E-graph for the four reasons, the four approaches to reason about this equality. Then we used the standard SMT-lib benchmark, which contains about 7,600 files, and we did the same experiment as before. So we ran it against time. We ran it to see how much time it takes for each approach. And what's obviously clear here is the very wide gap between the valued embedding and the unvalued embedding. And this really shows the kind of how expensive it is to reflect all of these axioms inside of the E-graph. Again, we did this also for memory by counting the classes and the nodes, and we got the same. So, in summary, invite you to read our paper. We have inside it an abstract and extensible E-graph framework, and the three approaches for handling disequalities, an evaluation to compare these things, and one more evaluation that I didn't get to show you. So with that, I thank you. I invite you to read the paper, and I'm open for questions.
Hi, thank you for the talk. I was wondering whether you knew why the valued embeddings were so much slower. Like maybe if you had a better data structure like union find, you wouldn't have to store as many things in the relation.
So you're asking about why this gap is so big?
Yes.
Yeah. So I will try to go back to just about here. So I kind of added these two things, right? So I would first of all have to duplicate them to do symmetry. Sometimes I would also need to add versions to handle reflexivity. I would need to reflect all of these things. I need to iterate on them because I might make progress, as in here. And while I make progress, I need to add maybe additional equalities. And so this step is iterative. It's not like a two-way process. So every time you add things, you have to check whether you can prove more things out of it.
All right, thank you.
Hi, thanks for the talk. Similarly, any intuitions on why Nelson wins?
I think so. So if you squint really hard here, what you will see is that these two edges, or rather the role that this node is doing, it's just to connect these two. It's just a way to connect these two, but through an E node which is useless and also has a useless E class attached to it. If I show you kind of this way, so this is a much direct way. In memory, this edge would just be a pointer somewhere inside of the E class, whereas here you would have to add this E class inside of the hash cons, inside of the list, and then also record the E class. So there's much more stuff to record.
All right, the disequality itself is not kept anywhere as an atom in the structure. The disequality itself is not kept as a term in the structure anymore.
No, exactly. Okay. So for the sake of the stream, I will repeat the question and let me know if that's correct. So you asked if the benchmark I did, probably for the SMT lib, or so if they reflect realistic data. So I did. If the question is whether I kind of run the same benchmark through, let's say, Z3, CVC5, and OpenSMT2, We did not do that because there's so many factors other than the treatment of this equality inside of the subsolver, which is why we kind of ended up writing our own. Ideally, and this is left as an exercise or for some PhD student or master student, is try to extract actually the implementation of the eGraph that they use and really benchmark just the implementation. This would be the next thing to do there.
Great talk, Tom Ball, Microsoft Research. So did you look at instruction cache versus data cache? Because I imagine layout of data structures plays an important role. That's been my experience from watching Leo Demora create like 10 different SAT solvers, and all the packing, it matters.
Yeah. So this is my intuition. My intuition is that, again, because I'm using this, what is it? This pointer here as opposed to this additional indirection, I think is kind of maybe more cache friendly. I did not look at it. This is purely speculation.
Okay. So
everybody in. Okay, are you ready? Okay.
Is the mic on? Yeah, it is on. Okay.
Okay, and we have slides.
Slides. Awesome.
Okay, welcome everybody to the type session. Our first speaker for the session is Brigitte Pienka, who is going to be telling us about a dependent type theory for metaprogramming with intentional analysis.
Right, thank you. So this is joint work with Jason Hu. This is in fact the work he did in his doctoral thesis. He defended in November and he wasn't able to come today. But my understanding is he's online and he's hanging out on the Discord channel. So if you have any questions after the talk, feel free to touch base with him. So the first thing maybe we should agree on is what do we mean by metaprogramming in this setting? Okay, so what I understand here in this talk about metaprogramming is that we want to write programs that produce other programs. And we'd like to also manipulate these programs within the same language. So typically, metaprogramming systems support at least 3 of these operations, but we also want to support the 4th one. So the first one is essentially quoting a piece of code, a program or an expression, and you get an AST back. So if you have x times 2, x is some kind of variable that is contained in this expression. Splicing, in our setting, we will bind this piece of code x times 2 to this variable c. And we want to use it here in a larger AST, where we then instantiate this free variable x with 0. And that gives us the expression y times y plus 0 times 2. Okay? And then we want to evaluate that expression. So we bind to this variable c this piece of code, y times y. We instantiate y with 2, and that will evaluate to 4. And last, we might want to do code analysis. We want to eliminate this pesky 0 times 2, which will eventually get away anyway. And we would like to maybe transform this expression into y times y. So metaprogramming is very popular. It's been a long history, and it's also popular in type theory. It's widely supported in proof assistants like Lean, Rock, or Acta. And there's a good reason for it, right? It eliminates boilerplate code. We can implement tactics. We can use proofs by reflection. So it is a good thing to have, right? But there's a but, okay? And the but is that when you look at these systems, let's say MetaCog or Lean or even Template Acta, some clever person, and I have a lot of admiration for them, they've implemented this facility quote, okay, which allows you to quote a piece of syntax that you wrote in this proof assistant, and it's being reified in a data type that is being implemented in this proof assistant. And that data type is something called like TM. It uses some kind of De Bruijn variables for modeling your variables. And in particular, it doesn't enforce anything such as well-scopeedness or well-typedness. And that is sort of like going against the philosophy, right? We believe types are good, and maybe we're even believing dependent types are even better. So why are we satisfied to have a representation of this piece of syntax as an untyped piece of syntax? So that means essentially if you have errors in your code generation, you catch them later on, not at generation time, but when you use them. But maybe more from a fundamental point of view, I would like to know what is actually that type theory we're using, right? I mean, it's not the calculus of construction, or it's not Martin-Löf type theory. It's actually this thing, right, that has also quotation in it. And I'd like to know what is that theoretical foundation. So that's the central question we were setting out in this work. What is a dependent type theory for metaprogramming that allows us to quote objects that might be open, that we can compose code objects, that we can recursively analyze these code objects, and we can evaluate them. and these code objects are well-typed. So let's look at a few examples, okay? So here's a very simple, simply typed example. We are doing multiplication generation instead of power today. Okay, so you get an input NAT, and you want to generate code that will add x n times. So if you have 0 as an input, then you generate the code of 0. If you have successor of m, you first generate mult of m that will add x m times. And then you splice it in, you rename the possible variable in that piece of code u with x, and you add x to it. So in the type theory, we also want to know what kind of equivalences hold. Okay, so here we have mult of 1 that would evaluate to this expression 0 plus x, this quoted expression. But it is a different abstract syntax tree than just having x. Okay? And mult of 2 will evaluate to something like 0 plus x, but it is, again, a different expression than x plus x. So when you run this code, okay, then you also have certain equivalences. So for example, here you would bind mult of 2 to this expression 0 plus x. You instantiate the x with 5, so you're actually computing 0 plus 5, which gives you 10. But you can also use code underneath a binder. Okay, that's the second example. So here we're renaming the free variable that is in this piece of code with y, so we get 0 plus y. And since in a type theory we're evaluating under lambda, this would actually then give you a function that adds y to y. So, and the last operation is we want to do code manipulation. So we might want to get rid of these pesky 0 times something. So here we're writing a code transformer. It takes in a contextual object, okay, where we have here an object nat that depends on this variable x, and we're returning a nat that depends on x. And we can analyze what the shape of y is. For example, it is 0 plus b, where b is our pattern variable, and in this case we return just b. And if we have a plus b, where both of these are pattern variables and might contain x, then we first simplify a, and then we splice it back in. And yes, there's sort of this renaming of this variable happening, so we are in a good world. Okay, and anything else, we just return. So then you can actually simplify your multiplication code, and you get this equation that indeed the simplified multiplication algorithm of 2 will be equivalent to x plus x. So, so this is essentially the goal of this Martin-Löf type theory. It uses as an idea layers. It's based on these ideas of contextual types. When we quote an object, we get a well-typed contextual code object. When we compose well-typed object. We can run well-typed code as programs, and we can pattern match on that code. So the key idea is really that we have layers. Okay? So the first layer is the layer of syntax, and that is code. In our case, really the syntactic representation of Martin-Löf type theory. There's no computation. So if you define nil, okay, which is a polymorphic list constructor, then you can define nil, which needs to apply to a type. So here you have lambda x applied to nat. And that is not equivalent to the syntax of nil of nat, because they're real syntax trees. Okay? Now you want to know what is the type of these objects. Okay? Well, clearly the first object has type list, lambda x applied to nat, because I'm just replacing the a by whatever type I had here. And the second object has type list of nat. But the question is, maybe on the level of types, we do want to identify these types to be equivalent, because in some sense types classify objects, and they're not really just syntax. And so in our type theory, we do allow reductions on the level of types, but not on the level of code objects. Okay? So that brings me to the second layer, which is essentially the Martin-Löf type theory we know and love. It has computations, in particular has beta reductions. Okay? So it's really exactly what Martin-Löf type theory is. And then we have a third layer, which extends Martin-Löf type theory with the ability to quote objects, to compose objects, do recursion on these objects, and pattern match on these objects. So now you have really a tower of these languages. They share the syntax, more or less. Okay? Clearly, the meta-programming layer extends Martin-Löf type theory with these constructs we have. But we also want to control the computational behavior, the equivalences we have at each of these layers. So that's exactly what we do. We have uniform syntax. We have a syntactic typing judgment that essentially is parameterized by what layer we're at, so we can control these equivalences. So I give you a little bit of a flavor of what this looks like. So this is a typing judgment. It is parameterized by this I, And this I is either code, a dependently type theory, or a meta layer. The gray part is coming from the universe levels we have to handle. Okay. And then usually in a type theory, you would say, well, T is well formed, and then of course this type and this context is well formed, and now the question is, are they always well formed at the same layer? And the important observation is that since we want to distinguish what equations hold for code versus types, we actually think of the code, which is here in orange, right, that for code we would not have equivalences, but it lives in this typing environment where we do allow equivalences to happen. And this function here essentially tells us how the object we're trying to type relates to its environment in which it lives. So when it's a meta-programming function, all of them are well-typed and well-formed at the meta-programming layer. If it's a dependently typed object, all of them are well-formed and well-typed at the dependently typed layer. Just at the code layer, we make actually that distinction. Now, the most important lemma we have is actually the lifting lemma. Okay, and that says that a well-typed object at layer I remains well-typed at layer J. And to give you an idea why this is important, I put up here the typing rule for PyType, or for applications. Okay, so this is code, T applied to S. And so S is code. Okay, S is of type capital S. But I said that this type here, right, here is actually is a dependent type, from our D layer, from our Martin-Löf type theory. So why can we use an object that is code on that layer that is D, that is sort of higher up? Okay? And that is basically justified by the lifting lemma. Okay? And similarly, for code execution, we have here a piece of code that is C, okay? But we're plugging it into an expression that comes from our M layer, where we have pattern matching and recursion and everything. And so why is this justified? Well, again, because we can promote or lift C up to that M layer. Okay. So this is really, really central to make this work in some sense. So our main contribution is then that we have a syntactic type theory with a non-cumulative Tarski-style universe hierarchy that supports quotation, composition, execution, and recursion of these type theoretic code. We have a uniform syntax. We have this layer that we have, so here we have 3, C, D, and M, and that allows us to control what equivalences will hold. We've proven weak normalization and the decidability of convertibility based on a Kripke logical style relations. So we define a reducibility candidate very similar to some of the previous work, some of our own, but also from Andreas. And in order to control sort of the complexity, because we have now 3 different layers and we don't want to do like 3 different kinds of normalization proofs necessarily, we introduced this idea of using pers. Okay, so that actually cuts down even Andreas's proof by half. Okay, so it makes it sort of manageable to do actually this proof. And we give some examples in the paper where we sketch sort of how we could use DLAM to write tactics similar to the simplifier I've shown you earlier. So, so I'm really fast today, apparently. Okay, so you can ask lots of questions. If you think about the spectrum of metaprogramming in proof assistance, you have on one side sort of this untyped representation of code. That's sort of currently the state of affairs in Metacoq or in Lean or in Acta, as well as in tactic languages like the LTAC. And then certainly, right, we were gradually moving to something that is giving more guarantees. So LTAC 2 gives more guarantees, MTAC gives more guarantees. But sort of what is this type theory that would give you really full guarantees, right, about the code you're writing that has been sort of elusive? And that's what DLAM tries to do. So what's next? Well, the next is really to implement this kind of this type theory, maybe revisit our choice of Tarski versus Russell-style universes in our type theory, and develop maybe an NBE proof for this language so we can actually get a good mechanization out of this work. All right. So we have lots of time for questions.
Yeah. Okay. Thanks for the nice talk. Do you think that you could use the universes and sorts to emulate your layers instead of having an explicit layer mechanism and rely on universes instead?
I don't think so, because of the fact that we want to control equivalences. So unless you can also control the equivalences somehow by the universe layer levels, which typically we don't. Typically we have the same kind of equivalences, regardless of what universe level we have. I mean, if you could, then I would say I'm hopeful.
I was more talking about sorts than levels. Like, if you have a sort prop, then you have impredicativity. If you have the sort S prop, then you have proof irrelevance. So there is some kind of new equality, and you could have less as well.
Yeah. So we would need to change probably the notion of equality, and then I think one could maybe emulate them. Yeah, that is true.
I was wondering if you've thought at all about extending this to sort of arbitrary layers of metaprogramming, so that you could have one metaprogram generating further metaprograms in the next stage, similar to, say, the staging in something like Racket.
Right. So, so in this work here, we were really trying to emulate or understand what the current practice of metaprogramming in proof assistance, like Lean, for example, is. And there you really have only 2 layers. Okay? Now, we've done some other work, in particular Jason has done some other work where he has a modal-dependent type theory, which has n layers, but it doesn't have pattern matching. Okay? And so the important part when you do pattern matching is, I think, a form of layers, because it gives you a very clear characterization of the syntax of the thing you're pattern matching on. Okay? So in fact, I would say it is essential that you have a notion that controls that. And if by restricting it to 2 layers, you get that control. Okay. Now, I should also mention we had a paper at ESOP, okay, where we describe a simply type version of this layered system. And there we do sketch an n-ary version. Okay. But if that is really useful in this setting, I'm not sure. Okay.
Okay, so just as a follow-up, it sounds like and I think this is what happens in practice in something like Racket, which is if I want n layers, I'm always working with 2 relatively. Like I'm always at 0 and 1 relative.
That's right.
Okay, thanks.
Yeah. And I would say actually a lot of programs where you want n layers, you can, if you have pattern matching on code, you can do the optimization you would otherwise do in multiple layers. Okay? So I'm not 100% convinced that it's always useful to have n layers in the theory. Okay? Because if once you have pattern matching, you can analyze the code that you have generated and you can optimize it. So one thing, for example, you might want to have multiple layers because you know that in the first layer you get a matrix that has zeros in it, and then you want to optimize, like depending on what the second argument is, you could optimize sort of certain multiplication or operations later on as well. But then let's just generate them, and then you pattern match and eliminate. Okay. So I think there is something to be understood about this trade-off of writing your own program transformations versus doing n-stage multi-stage programming. You see what I mean?
Yeah. Hi. Speaking of pattern matching, in practice, we usually need different notions of equality for different purposes, right? Sometimes you want to match the syntax really on the nose. Sometimes you want to match up to alpha equality. Sometimes you want to match up to definitional equality. Can you see that being integrated into this framework as well?
So our experience is you basically have to make a decision, right? So in this work, we made this decision that what code is pure syntax. So there's, you get alpha equality, but no other definitional equality, okay? Now, we have a paper at JFP, okay, where we made a different decision, and some of the reviewers didn't like this, okay, where we do allow definitional equality on the object that we're generating, okay? And I think that is perfectly fine, especially if this is just thought as a black box generation. If you want to do pattern matching, though, I think you want to know what the syntax is you're getting that you're pattern matching on. And so I think there is a good reason that if you want to support pattern matching, that you don't want to normalize the code that is inside the box, okay? And that, because you can always write it, if you have pattern matching on code, you can write the normalizer. You can write the vkit normal form if you really want to put it in a vkit normal form. So yeah, so I think there's this trade-off, okay? And I think a lot of it has to be decided once you actually want to use it. But for pattern matching, I do think you want to know the syntactic structure of the thing you're pattern matching on.
Okay, that makes a lot of sense. Thank you.
Okay, let's thank Brigitte again and switch to Jessica.
Great.
Are you ready? Okay, so our next speaker in this session is Clément Baudot, who is going to be telling us about a new extension of the ML.
Thank you. So hi, everyone. My name is Clément Baudot. I'm going to present the result of my PhD thesis, basically, that I've defended last month. Okay, so let's start with a bit of context on ML modules. Allows me to? Yeah, okay. So let's start with a bit of context. What I mean by modularity is, I would say, the hard form of being able to identify natural boundaries inside programs and gather components that make sense together inside what we call modules, and to identify also components that can be reused throughout the system. The tools for achieving this are basically the ability to define, control, and enforce interfaces, the ability to abstract part of the code and consider things as black boxes, ways to control namespaces, and finally, ways to combine the different modules that you've built through what we call composition. In programming languages, that takes a lot of different forms, functions, interface files, libraries, but there are, I would say, three main approaches that provide the whole set of tools for modularity, which are the object-oriented programming, type classes, and the module system, the one I'm going to focus on today. So let's do a super quick introduction on ML modularity. Let's define a library that handles complex numbers as a pair of floating point number. So we can gather all the definitions of our library inside a structure that is defined with those keywords, struct and end. And we can put inside this structure as many type definition and value definition as we want. Then we can access the content of a structure through this dot notation outside of the module. We can then define interfaces that are called signature in the ML nomenclature. And here we can define the interface of a mathematical ring where the type definition is left abstract. And we can use this interface that we've defined to restrict the outside view of the module. And if we do so, then the rest of the program doesn't know that complex are implemented as a pair of floating point number, and the type checker would refuse to consider this invalid polar representation as a floating point number. We can also use interfaces to enforce polymorphism, and we do so by defining what we call functors, which are not the category theory thing. And a functor is a module that takes as input another module. Here it's polynomial implementation over any ring. And as you would expect, we can call the functor on the complex module. But we can also realize that the polynomials themselves form a ring, and we can get the sets of polynomials with two parameters by just calling the functor again. So the main takeaways is that we have a separate language layer. The module layer is a separate language built on top of normal core level OCaml, or ML in general. And basically, modules are a small calculus with records and function and explicit type ascription. And the thing that makes them a bit tricky sometimes is the fact that you have types within terms, basically. So you have those type definitions, and they can be abstract and they are within the terms. And you have this telescope mechanism where once you've defined a field within a record, it's accessible through the rest of the record. So it's not dependent records per se, but it's a form of telescopes. And also note that the way we separate the different fields is only with spaces. There are no like semicolon or anything. Okay, so what's up with OCaml modules then? So the OCaml modules are quite renowned for having rich abstraction mechanisms and being quite extensively used in practice. And also there are new features that are being actively developed and that I think are quite exciting. But the problem is that the specification of what's going on in OCaml kind of dates back to the late 90s, so it's a bit out of date. And when you have an out-of-date specification, it means that at some point you have unsupported edge cases that start to pop up. The system becomes harder and harder to predict, and also harder to use in some advanced cases. And so the goal of this work, and basically of my thesis, was to try to build a specification for OCaml modules that would not have any of those issues, but could also be used to retrofit the existing type checker. Not just replace it with a new thing that would be perfect, but retrofit the existing. So what I mean by it's a problem to have an outdated specification. Let's look at a couple of examples. There is a property that I like to define as robustness, the idea that there are some changes that are semantically equivalent, and they should not break the type checking. And it's not the case in current OCaml at the module level. Let's look at this example. It doesn't matter, but the thing is that I'm going to do a beta reduction and inline the definition of the module X, and then the type checker will refuse this expression. Sadly, type checking is also not stable under beta expansion, where you have some code, not very important, but it type checks, and you add an intermediary definition, and it breaks the type checking. The two problems come from very different aspects. The first one is what we call signature avoidance. The second one is the problem of module identities. And in this presentation, I'm only going to focus on the first one. So let's talk a bit about the infamous signature avoidance problem, at least infamous in the ML module community. So it comes from the interaction of three things. First, we have those abstract type fields that I've shown before, very important to enforce invariance. Then we have these dependencies within the fields of a signature because of this telescope that we've seen. And we have also operations that are going to remove fields of a signature, and they will create dangling dependencies, basically. So let's look at an example that is basically an instance of the previous one. We have two modules, N and M, and I'm going to inline the definition of N. N contains a type definition, T, and then a submodule that mentions this type definition. And if I do inline the definition of N inside of the definition of M, then there is a reference to this type T that has gone out of scope. And the type checker doesn't know how to resolve this reference, so it fails. So this is a problem, but it's OK because we have a failure. What's more worrying is that we also have silent errors, so what we call over-abstraction, kind of a similar setup where we're going to inline the definition of the module N. But here we have just type definitions, and the type U and V are equal, both equal to the type T. And if we inline the definition, then the type checker accepts the new definition, but it has abstracted away the definition of U and V, so they are no longer equal. And so the goal of the goal was to say, okay, we don't want over abstraction, and if possible, we also don't want to have any type checking fail when we have fields that go out of scope. So that's the problem that ZipML is trying to solve. And let's see how it works. So let's go back to the first example where we have a type definition, and again, OCaml would fail on that example. So let's take the signature that we have before we do the projection on the submodule X. And basically, it's a tree-like structure where we have dependencies between some of the part of the trees, and especially the value X mentions the type T. So of course, if we just project by removing the fields that are no longer visible, we create this dangling dependency. But there is a classical technique in functional programming if you want to focus on some part of a tree-like structure without losing the rest of the structure. And this technique is called the zipper. And the idea is that you would not throw away the part of the structure that you're not interested in. You would keep it on the side. You would basically invert the arrows. And so you keep all the type information that you need in order for the resulting signature to remain valid. So what ZipML would output in this context would be that the module M only contains a value X, but also has an attached zipper where the type definition is preserved. And that's basically that's all there is. We extend the signature language with this notion of zippers, where the zippers, they act as a hidden typing environment that is attached to the signature. But if we do so, then if we only do that, then every operation that might create dangling dependencies will create new zippers that might pollute the resulting signature. So we also have an operation that we call zipper simplification. So I'll just make the example a tiny bit more complicated, where we have two type definitions. And we have a module X where we have a type definition and then a value definition. So again, OCaml would fail on an example like this because X would be hill typed. So in ZipML, what we would do is we gather all the components that have gone autoscope with the projection, and we put them in a zipper. And then we might realize that, OK, so type T is abstract, but type U is just an alias of another type definition. So we might as well inline it, right? And if we do inline it, then we see that U is not used anymore in the visible part of the signature. So we might as well get rid of it and garbage collect, basically. So that's the first part of simplification. And then we might go a step further and say that we have T and V that are both equal. There is one that is the definition point and one that is a copy of it. But we could invert those type definitions. And we get something that is equivalent, where it's V that is abstract and it's T that is equal to V. And if we do this transformation, then again, we realize that the type T no longer appears in the resulting signature. So we might as well get rid of it. And we end up with this signature that is equivalent to the first one, but is also valid in the source syntax. So basically, OCaml could have found this signature. And so that's I think that's the power of ZipML. Is we use zipper to prevent avoidance, and then we use simplification to go back in the source syntax if we can. So just a glimpse of what it looks like to what ZipML looks like on the inside. So we have a projection rule where we can take any module expression X module expression M, sorry, that contains a submodule X, and we can project onto it. We just gather all the fields, the declarations that the module might depend on, and we put them in a zipper. And this is typically a rule that is very problematic in systems that don't have zippers. We have a zipper removal through subtyping. So if you have a module that has a zipper signature and you do an ascription to force a normal signature, then the zipper disappears. And this is in the normal workflow of an OCaml developer. This is typically what happens when the result of the inference of the ML file meets the MLI file. So the idea is that ZipML is not implemented yet, but if it were, probably most of the time, the developer would never see the zippers. And finally, we have this floating garbage collection of useless fields with a mechanism of simplification. And we also have a theorem stating that the simplification that we do actually never prevents further typing. So we never have this over-abstraction where we might lose visible type equalities. The main properties of ZipML, of course, is the soundness, and it's obtained by linking ZipML with previous works, and especially M-omega, which you can find in the OPSA 2024 paper. That is basically the latest iteration in a very different line of work, where ML modules are understood via elaboration in F-omega. And so there is a soundness theorem that is what you would expect. And it's obtained by elaboration of ZipML in M-omega. And there is a conjecture, and conjecture is not because we're not sure it's true, it's because in France, PhDs are 3 years, and so I didn't have time to finish the proof, but I think it's true. So we have a conjecture that M-omega, so maybe the standard approach to typing module systems, and ZipML, that is more of a custom approach to typing module system, actually have the same expressivity, meaning that the zippers that we use the zippers that we have can be used to represent quantified variables and the mechanism of extrusion that you have in the Effing line of works, basically. So you have this kind of big picture of OCaml on one side and F omega on the other end. And we have links that are quite strong between the intermediary points. OK, so let's sum up. So I've presented quite quickly ZipML, a robust type system for OCaml module that doesn't have the beta extrusion and so the two issues I've shown before. It uses internally syntactic signatures. By syntactic, I mean source signatures just extended with this small notion of a zipper, which is the same as the current OCaml type checker does, basically. And it solves the signature avoidance problem with the introduction of zipper signatures. There's more to ZipML in the paper. There's actually quite other aspects that I have not developed in this presentation. The first one being the mechanism of module identities that solves the second problem that I've shown. That is approached with the notion of transparent signatures. In ML module systems where you don't elaborate into F omega, you have the problem of strengthening that is also quite infamous. And it is solved in ZipML I think, in an interesting way with laziness built in. So the type checker would not do unnecessary work. And finally, we have a mechanism that is often overlooked, is the preservation of user-written definitions. So as I've shown in the first example, the user can write some type definitions, intermediary type definitions. And in most formalization of ML modules, those are just inlined away. But for practical purposes, they are very important, especially because the type expressions can be very big. So yeah, ZipML has a mechanism of normalization and keeps all those user-written type definitions. And the most obvious future works are to get it into OCaml. And also to maybe do some user surveys, understand what are the practical heuristics we need for the rewrites. Sometimes you can remove a zipper by inlining all the type definitions that they are in, but this would explode the size of the signature. So sometimes maybe you don't want to inline the result. And those are the kind of practical heuristics that we need to explore. And I finished by saying that you should watch the research space of ML modules. There are new things that are coming, and I think they're pretty exciting. Thank you for your attention.
Okay, we have time for questions. I have a question. Is there an interaction between your extension and error messages? Right. Have you thought about whether it makes them better or worse?
That's a very, very good question. So the other approach that I've mentioned, the M omega approach, technically has the same expressivity as ZipML. So you could use it as a replacement of the type checker. But one of the things that we were worried about is the fact that it would probably produce very obscure error messages. Whereas with ZipML, if you have a situation where you need to simplify the zipper away and you cannot, you would have precise program points that you have user-written names, and you could produce an error message that would be understandable by the user. At least I believe so, because I have not implemented it yet. But it seems well suited to have good error messages.
Okay. We have some more questions in the back.
Hello. Me?
Yes.
Yes.
Yeah.
Hi.
Yeah.
Maybe OCaml has formatted my brain too much at this point, but I can see the case where simplified away, but that like this mic. But yeah, when there needs to be a type left in the zipper, like that type definition should be there in some way, and so wouldn't it be better to rewrite your module?
So the key idea of using zipper is that you can delay the point where you actually throw the error, and if you have to print the result of the inference to the user because it tries to extract the MLI file or is doing module type of this kind of things, then if you were not able to simplify, you would have to throw an error. But you wait as long as you can, because sometimes other operations on the module makes the fields that you've kept in the zipper useless.
Ah, so it's not something you would keep in your ML or MLI file?
No, it would not. The idea is that it would not appear in the MLI. The user is not able to write zipper signatures. It's just the internal representation is made flexible. And so the type checker doesn't have these weird syntactic rules that it currently has to prevent types from escaping scopes.
Got it. Cool. Thanks.
Thank you.
Okay, we need to get the next speaker up. Right here in the back, we have time for one quick question while we switch.
I'm not too familiar with the camel modules, but does your mechanism might be preventing some legitimate intentional uses, like some hiding of the types or not, which users might have done because they wanted to do it, and your scheme will eliminate them because they think it's errors?
So that's a very good question. The way it works is that if the user wants to lose type definitions, he can, and the user can abstract type definitions, and it can hide internal details of the module. But what's going on right now in OCaml is that sometimes those definitions are hidden away implicitly, sometimes it doesn't work. And with ZipML, you have a clear specification of when does the actual disappearing of fields actually occurs.
So it might break some existing code, maybe not really.
No, I think it would be fully backwards compatible, except if people used. No, it would be fully backwards compatible. You cannot use the fact that you would know that two types are different. You can only use equality.
Okay, thank you. Okay, the third speaker of this session is Junji, who is going to tell us about bidirectional higher rank polymorphism with intersection and union types.
Okay. So is everything working in the audio? Okay. Hello, everyone. I'm Shinji, and today I'm glad to talk about bidirectional higher rank polymorphism with intersection and union types. This is joint work with Chen Cui and my professor, Bruno Oliveira. So this talk will be divided into 4 parts. The first is a general introduction to the background, and secondly, our system, we call it FEIU. And third part is how to formalize this system, its correctness in the work prover. And the last part is the conclusion summary. So let's first go into the background to introduce some notions and concepts that may not be very familiar to the audience. The first thing I would come up with is the high rank polymorphism. I think maybe it's the most unfamiliar concept. So it can be viewed as a generalization of the parametric polymorphism existing in the Hindley-Miller style type system. Where in Hindley-Miller type style system, you're only allowed to write this kind of polymorphic types where the quantifiers appear in the top level. So you cannot represent a function that takes a polymorphic function as an input. That generalization somewhat mitigates this problem, but it's still not general enough. So you want this for all quantifiers to really appear in arbitrary types. So we have this notion of high rank polymorphism that allows the four quantifiers to appear inside function types. And the rank n polymorphic type is a function type that with a rank n minus 1 type as an argument. And here are some examples of rank 1 and rank 2 types, and you can make arbitrary rank types just by nesting them inside. And the second notion is intersection union type. Because these things usually have a very clear theoretic interpretation, so it's usually most people have a very clear intuition about it. So a term has an intersection type means it has both types. A term has union types means it has either types. And these subtyping rules characterize this theoretic notion. In more complex systems with intersection union types, you sometimes have more complex subtyping rules with, like distributivity, but we don't consider them here. And these two sets of features were studied independently by various of works, but their interaction or combination was rarely studied. But we think it's an interesting problem for various reasons. First, they are both core features of several mainstream languages like Scala and TypeScript. In TypeScript, you use these intersection union features to represent heterogeneous list, mixing patterns, overloading, and various other patterns in dynamic languages. In Scala, intersection union types also appear in the dot calculus. And I don't have to mention the necessity of parametric polymorphism here, I guess. And secondly, in recent studies, people find that their combination is expressive enough to type a large portion of dynamic language. You don't need gradual typing, but you already use these features. You give static types to a large portion of programs. A second, parametric polymorphism and intersection types are both important mechanisms to represent polymorphism. One is closed word, one is open word. And the last thing is the explicit type application. It complements the above two features very well because it allows programmers to provide complex and ambiguous instantiations. Like for a lot of systems, you cannot do full inference. You really want the programmers to provide some help to the type inference engine. And also, these features are also supported by most languages because in a lot of languages, you don't even have this inference, so you need to the programmers to provide them anyway. And for this complex type system to work, we must have some sort of type inference. And type inference itself is an ambiguous notion because people mean different things. Here, we are not so ambitious to mean that Hindley-Miller type style inference that we infer all types from no notation. We are in general interested in two cases. The first is implicit instantiation, which again, in general consists of two cases. You want to apply a polymorphic function to a specific argument, and you want an argument with a more general type to be regarded as an argument with a more specific type. So in both cases, we want these instantiations to be automatically inferred by the type inference engine. The second rule may be a little bit weird. The second case may be a little bit less sane because it requires the idea of polymorphic subtyping. It says a polymorphic type is a subtype of another as long as you can find the proper instantiation. So we use a different symbol tau here because in a lot of cases, this instantiation is not a full type set. We only want a subset of the type to be automatically inferred. We have this quite widely used dichotomy, which is first is predictive instantiation, that the instantiation itself only consists of monomorphic types. The second is they are allowed to contain arbitrary types where the instantiation themselves can be polymorphic. For example, in this case, we instantiate this A with this for all A to A, so the ID function can be applied to itself. We are also interested in some sense of inferring simple functions without annotation. So when a function has a monomorphic type, we also want to avoid the annotation burden. So we use a bidirectional framework to do this. The bidirectional framework in general consists of two modes, the inference mode or the synthesis mode, where this type A is the output. You only examine the expression, and you won't get a type. And you also have this checking mode. You both have this E and A as input, and you want your algorithm to check. So the inference and checking alternate between each other. You get the result of the whole algorithm. Next, we will go into our system. So we have this philosophy that's infer easy, or in our sense, it's predictive instantiation. But we allow programmers to provide all the imperative instantiations so that we don't lose any expressivity. It can be viewed as an extension of previous work by our group to support first-class intersection and union types. So actually, in a later stage of our research, we find that our system is quite similar to how actually the algorithm in TypeScript works. They seem to, based on our observation, we don't really have the proof because we don't really check its code, but based on its behavior, we think TypeScript seems to be loosely based on Dunfield and Krishnamurami's ICFP 2013's work with certain ad hoc design choices to support intersection and union types, as well as has more other features in TypeScript. But since our study is a formalized study, so our system provides a more disciplined treatment, and it has the following advantages. It supports all the relevant quantifier, and thus we have the checking subsumption properties for the type system. We also support more complete overloading, and we have less syntactic restriction on writing polymorphic types. We also support intersection introduction rule and the monomorphic function inference, as we mentioned before. We also have the guaranteed monotype instantiation, which is a corollary of the completeness of our algorithm. So most of these concepts are self-explanatory, and we have more examples and text in our paper. But one thing that may be not that self-explanatory may be the first one. So in general, it is known that all the irrelevant quantifier is incompatible with explicit type application, because with explicit type application, the instantiation is bound with a certain quantifier. So it doesn't make any sense if you swap the the order, and this thing should still work. But it turns out that TypeScript, because we guess it's based on decay, it still takes this approach. Okay. So it loses the property of checking subsumption. That means if your program's type checks, you want to replace the type with a super type, the type checking should still succeed, but in this case, it fails. Okay, you don't have to lose that. You don't have to look at the concrete example, but it's basically what the idea is basically what I mentioned here. So let's look at the rules of the system. This was original rules of the elementary type inference. We have unit type, the type variable, the subtype variable, which we will introduce later, the for type, the function type, and also top and bottom type. And you also have this type abstraction and type application. So as we mentioned before, since we have type application, we want all the relevant quantifier that rejects this kind of subtyping, where these two types only differ in the order of the quantifier, but we don't want the subtyping to hold between them. And also, it has a restriction on the polymorphic type. It only allows full real polymorphic type, that you don't allow this for a int, which is basically the same as int. So to achieve the first one, we need to modify the subtyping rules. This is the for L rule we mentioned before. This is the for R rule. So it says we can extract the type variable on the right-hand side to the context, and this variable may be used by this tau later, by later invocation of this for L rule. So instead, we change this rule to only compare two for all types. And also, we introduce this subtype variable, which is not a monotype, so it will not be used by later instantiations of for L rule. We also add a restriction in the for L rule to say we always prioritize this rule over this rule when both sides are for all types. The syntactic restriction is easier to implement. We just add more conditions in the well-formedness check to ensure the formation of types and expressions. With the introduction of intersection types, things actually become trickier. Because in the subtyping of intersection and union types, you sometimes discard one branch. So it makes some checks useless, because sometimes you perform a check before and this branch is just discarded. So in this case, for the intersection type, we need this type variable to appear on both sides to make no counterexample happen. For union types, things are still usual. You only need this type variable to be mentioned by one branch. So it means this type is well-formed, and this type is not. So this is the subtyping rule. The new things are marked blue. So the black things, I think they are rather standard, like bottom types, type variables, function types, and the for all rules and for all rules mentioned before. The subtyping rules of intersection and union types are also standard. The only thing left here is what syntax restriction should we put here? If we put the old thing, the thing doesn't work, we have an intransitive subtyping relation. It's basically because you can have a type which is not a for type syntactically, but it's equivalent to a for type. It's just you can use intersection union types to bypass this syntactic check, and you result in an intransitive subtyping relation. So the simplest thing to avoid this is that we put a very strict restriction to say that we don't invoke a for L rule when B is a for type, intersection type, or union type. It works, but it's too restrictive. It rejects too many things. Even though for all rules will not be invoked later, we still too eagerly decompose the right-hand side. So what we want is a similar asymmetric syntactic restriction, just as the free variable check before. And when we have this syntax check in the for L rule, we still have good subtyping, and we have more expressive subtyping. So this subtyping now holds. And you can find the implicit instantiation to be int. This is the typing rule. So the typing rules is in the bidirectional style, and we add these three rules for the checking rules of intersection and union types. This is the intersection introduction rule, and we still need this because we have a restricted inference ability, so sometimes we still want to relay the type information to the inner expression. And we also have these two auxiliary judgment here. It's basically can be viewed as constrained inference, which you want to make sure the inferred type has a specific shape. So it has, in this case, it should be of a function type. In this case, it should be either for or bottom type. So it can be applied or type applied. And we can have a glimpse on our algorithm presented in the worklist formulation, that we have this automatic scope management. And we also turn our guessing of instantiations into constraint solving and generation. This is one case of generation, and this is two cases of solving. And we also use continuation passing style to to delay some information that we don't know, but we need to create the judgment here. So when we infer the type of E, we will make it a subtyping judgment and to perform later check. So let's slightly have a quick look at the formalization. So one big difference is that previous works in this line of work usually use Arbella. Arbella has built-in support for bindings, so it's very easy to use in that sense. But we turn to Rock, so we also need to use a new infrastructure based on locally nameless style, and we use Alt and L engine to achieve this. And this is a proof structure that with properties proved in each system, and the arrows indicate their relative soundness and completeness. Here, soundness and completeness means whether they infer the same set of programs and type check the same set of programs. We also have introduced this intermediate worklist to bridge the gap between these two systems, so it makes the whole proof simpler. So these are the properties formally speaking. So we have subtyping transitivity, we have checking subsumption, and we also have type soundness by elaboration to a type sound system, which is a system F with record and product. With product and sound, sorry. And we also have the soundness and completeness of our algorithm. Basically, it says what our specification states, our algorithm will succeed, and what our algorithm succeeds, it also follows the specification. And our algorithm is also decidable. Here we state this in a more specific version where expressions are closed on the empty context, but actually when we prove them, we need to generalize to the open context and worklist. And since we move to locally nameless style, actually it motivates us to rethink a lot of decision choices made before about the formalization. One thing we mentioned here is the transfer relation to relate the algorithmic worklist and the intermediate worklist. So here we need to define this transfer relation to interpret, because this thing only exists in the algorithmic worklist, so we need to interpret this thing as a word form declarative type. And previously, this was a transfer relation used before. You can see it examines the worklist from beginning to the end, which contradicts to the usual inductive structure of a list. And it also has substitution everywhere. And it really complicates things a lot. And instead, we develop a syntax directed transfer that makes things much simpler. So basically, the general idea is we kept track of explicit substitution set to track all the instantiation, and we don't do the substitution eagerly. So this is the rules. They are quite structural, so we can just skip over them quickly. And also, we have other design choices. Basically, we have a defunctionalized version to represent the continuation parsing. So everything can be inductively defined in Cork without further proof burden. So let's go to conclusion. So this is a summary of the contribution of our system. We have a bidirectional system for high-rank polymorphism with intersection and union types, and it has good properties. We also had a sound, complete, and decidable algorithm for this system. We then started two extensions in our paper. The first one support record, and the second one both support record and a relaxed monotype definition. So all the things are formalized in Cork, and we also provide a prototype implementation in Haskell. Thank you, everyone. And questions are welcome.
Okay, we have time for some questions.
You mentioned something about deriving monotypes when they exist. So could you clarify, is it like if there exists a monotype instantiation, you're guaranteed to find it by your inference algorithm? Or
No. It's just we don't need this as a premise to make sure. It's just if our algorithm finds one, it means there exists one by the specification. And if the specification guesses one, it means our algorithm can find that.
Okay, so it sounds. You said if
and
there
if
exists,
there is
then you
no,
can also find
if the specification cannot find one, well, it means this program will not be type checked by our specification, so it should be rejected. So our algorithm will also report an error in this case.
Okay.
Yeah.
And then I had another question. The slide had something about more expressive overloading. Could you clarify, sort of more expressive compared to what, or Is it just because you allow for high rank polymorphism, now you can have overloading, which has also high rank types? One of the first slides with the contributions or
I think it has similar expressive power to TypeScript. You basically based on, or in Flow, you actually have more complete, let's say, constraint solving, because TypeScript based on DK, they use a similar solving strategy as we do. But Flow and maybe Scala 3, they gather more constraint and you solve them laterally. So you can have, in certain cases, better solving solutions. But we do have very similar expressive power with TypeScript, let alone other features in TypeScript. Yeah.
Okay, we can take it offline. Thanks.
Okay, let's thank you again. Thanks. Oh, it's just there. Give it a sec. Okay, you ready? No. Okay, our last speaker of the session is Tara, who's going to be outbreak temporal effects.
Okay, thank you. So this is a joint work with Hiroshi at Tohoku University. So in this talk, we will study the temporal verification, especially linear time temporal verifications. The aim of the linear time temporal verification is to verify the traces generated by the program. So in this case, the trace means that some sequence of the effect or event triggered by the programs, and it may be infinite, right? And there are two major classes for temporal verification properties, and one is safety properties, which means that no trace reaches to undesired state. So another class is liveness properties, which states that any trace can be extended to a desired trace in the future. Okay, and there are many applications of the temporal verifications, including resource usage analysis, access control, availability, and so on. Okay, so let me show one simple example. Here it defines a recursive function f, and it takes file names and just opens the file, reads the contents, and close the file, and then the function is called recursively. So if we are interested in the use of the file manipulation operations, then here the trace generated trace consists of the three effects: open, read, close. And in this case, by calling this recursive function, the infinite trace like this one is generated. Here open, it just consists of the infinite repetitions of the open, read, close, and so on. Right. And for the one example of safety properties for file manipulation is that the file should be the read and close only after opened. So such properties can be checked by verifying that some undesired trace is not generated. And the examples of the liveness property is that the file will be closed eventually after opened. So such properties can be checked by verifying that some desired trace should be generated after opened. Right. So in our work, we are focused on temporal effect systems, which is a type and effect system for linear time temporal verifications. And yes, and the temporal effect systems have some benefit types oriented by the type systems, like the higher support for higher order functions, type-based abstractions, compositional verifications, and so on. And the temporal effect systems have been studied so far for the, some programming features like the recursive functions and faster class continuations. But the current current temporal effect systems have some limitations. So the first limitation is that the temporal effect systems are specialized in only in recursive functions. So then it is unclear how we can address the more general recursive structures. The second limitation is that the existing temporal effect systems are specialized in some specific form of a temporal effect. So like in some work, the temporal effects are described using fixed point logical formulas or automata. But if we want to use another representations, one needs to redo the proving work, like proving the soundness theorems. So of course, it is not a desired situation. So the open question is that how we can abstract these different effect representation to a more uniform or abstract representations. All right, so we answer these in this work. We answered these questions. For the first question, we extended the temporal effect system to recursive types. So as you know, recursive types are very expressive and general programming features. So by extending with recursive types, we can implement many programming features and paradigms like the object-oriented programs, cooperative schedulers, and recursive structures. Right. And but the challenge in this extension is that the reasoning about the infinite behavior becomes much harder. So it looks like the infinite Leibniz properties. So because the use of the recursive types incurs some more complex recursive structure. So it is a very challenging problem. And we solved this challenge by using guarded recursive types with a later modality. Right, and for the second questions, we introduced a more abstract form of a temporal effect. And actually, it is just provide only algebraic structure of a temporal effect. And we also assume that some operations are necessary to, for sound reasoning in temporal verifications. And we also provide some two instances of this algebraic abstractions. One is based on omega regular expressions, and one is based on fixed point logical formulas. All right, this is a summary of our work. So let me explain the more details of our work now. So first, I will start with a background of the temporal effect system. So the temporal effect system provides some special form of effect called a temporal effect. And, but the temporal effect is just a pair of finite effect and infinite effect. And the finite effect represents some a set of finite traces, like the regular expressions. And the infinite effect represents a set of infinite traces, like the omega regular expressions. And the soundness of a temporal effect system means that assigned temporal effect over-approximates the actual behavior of a program. So if the program generates some finite trace, then the generated finite trace should be included in the interpretations of the finite effect. And if the program generates some infinite trace, then it should be included in the infinite effect, right? And yes, so for the examples I presented in this talk, this example satisfies this temporal effect. So it means that this recursive functions satisfies safety and liveness property for files. But if we insert some non-terminating computation before closing the file, this liveness property is broken. So because opened file is not closed. So then temporal effect can reject these examples by soundness. All right. So, but a challenge arising in giving a temporal effect system is in reasoning about infinite behavior. So infinite behavior is, in general, infinite behavior is defined co-inductively. So here I use the functions, new operations, which means that which returns the greatest fixed point of some monotonic function f, right? And using this greatest fixed new operations, we can, for example, define the non-termination behavior of the programs, like this one. And the problem is that how we can check infinity effects over-approximate the infinity behavior. So this is necessary for soundness of the temporal effect. But yeah, and in other words, so infinity effect iota should be an upper bound of the actual behavior defined by nu f. But the problem is that nu f is defined using the coinduction, but the coinduction principle is not useful in this case because it only allows under approximation. So, but we want to show that is an over approximation. So coinduction principle cannot be used in this case. So the solution in the existing temporal effects system is to take the greatest fixed point as an infinite effect. So in this case, especially greatest fixed point of the q, and here q is the upper bound of the function f, which defines the infinite behavior. Then it is easy to show that the infinite effect nu q is an upper bound of the actual infinite behavior described by the nu f. But the price of this approach is that now infinite effects are no longer invariant. So for example, in the usual type system, so the typing rule for recursive functions can be assigned by assuming that the return type, the function type is invariant of the computations. But now we cannot use this standard typing rule for temporal effect reasoning. And actually, the previous work provides some special typing rule for reasoning about recursive functions. So in that sense, we need to take a special extreme care of reasoning about the recursive structures. And but one of the issues in the previous work is that the existing temporal effect system only supports only a restricted form of a recursive function. So it is unclear how we can determine the infinite effect for the more general recursive structures like the recursive types. Yeah, and the second issue is that the representations of the infinite effect relies on some specific operations, like the omega operation in omega regular expressions or new operation in fixed point logic. So it is an open question how we can choose a suitable representation depending on the situation of the user. And to solve these issues, first we introduced the guarded recursive types with the later modalities, and we use these recursive types to extend to the temporal effect systems. And recursive types is just a very standard form. It's just it provides some standard operations of fold, unfold, and fold. And the later types means that intuitively it means that there are some later computations in a sense. And the next constructor means that its argument m is a later computations. And it also provides some operation like add to apply to manipulate some later computations. But I don't go into the detail in this talk. And furthermore, what we support guarded recursive types means that the type variables bounded by the recursive types is guarded, which means that alpha, type variable alpha, can appear only under the type constructor, later type constructor. So by under these assumptions, the later types and the later computation means that unfolded computation in a sense. In the terminology of the recursive types. So for example, the stream-like types can be given, like the above type here. But the below type is not valid types because the occurrence of the type variable is not guarded here. And for the fixed point or combinator, the recursive part, recursive call part, recursive argument part should be guarded here because it corresponds to some later or unfolded computations in the context of the guarded recursive types. All right, and we utilize these guarded or recursive types for sound reasoning in temporal effect systems. So the key observations in guarded recursion is that first generated infinite trace is split into infinitely many finite traces. And these finite traces happen between the successive some unfolded computations. Or in other words, it happens between the successive next guarded computations. So let me explain more details using these examples. So now I assume that the program M is well-typed and it generates some infinite trace. And first, such programs can be evaluated to the term like this one. Here, E1 is just an evaluation context, but the argument of M is the non-terminating term. So this M1. So next, the evaluation go to the evaluation of the M1, and again the evaluation of M1 reaches to the similar form like this one. So here, argument M2 of next constructor is also non-terminating, and by this under divergence behavior, infinite behavior over programs in guarded recursion, this process is repeated. So then we use this. So then we can use some infinite behavior. We can structure infinite behavior using guarded recursion types. And next, I explain how we can utilize this phenomenon, general phenomenon for sound reasoning. First, our idea is that first we infer some upper bound phi of the generated finite traces, and then we can view this infinite computation is more abstract, like this one here. So first, M generates some finite trace W1, but the remaining computation just repeat some generation of some finite trace in phi. Okay. Then we can take the infinite repetitions of the upper bound phi as an infinite effect. Then we can ensure that the originally generated infinite trace is contained in the infinite effect nu q here. And the remaining problem is that how we can infer the upper bound of the finite traces. And for that, we introduced some temporal effect forms augmented with some special operations. And and this is algebraic formulations of our temporal effect. But in this case, in these representations, the algebraic effect is just a pair over finite and infinite effect, and with some additional structures. But the first four structures are fairly standard ones to model the sequential effect with sub-effecting. So I will skip this one. The special operations are last two operations. The rate operations is effect level operations for rate modalities. And the role of the rate operation is to accumulate finite traces generated by the non-terminating programs. And we can achieve this accumulation by introducing this typing rule, and where the rate operations is applied to the infinite effect of the guarded term M. And then we can ensure that if the program, well-typed program generates some infinite trace, then the trace is split into the infinitely many traces. And the assigned infinite effect can recognize the traces and where the next guarded happens. Finally, we assume some operation fine, which it returns some which assumes that returns the upper bound of the accumulated finite traces. then we can use the we can do the sound raising these under these assumptions. Yeah, and our soundness theorem is just a summary of what I explained in this talk. Yeah. Okay, so we also discussed some examples and instances of this algebraic temporal effect. But right. Yeah, thank you so much.
Yeah, right here.
For the mic. There are two ways to compute fixed point of tracers, infinite tracers. You take all of them, you eliminate the one that don't work. And the other way, you take prefixes and you pass to the limit. You use a second.
Yeah.
And then you have a problem that what is true of all prefixes might not be true of the limit. And so why is your type system guaranteeing that the fact that all effects were proved correct for finite execution, why is it still valid when you pass to the limit? You must have something somewhere that I did not see.
I see, yeah. So maybe, okay, so I'm not sure I can answer your question well, but maybe one observation is that first, infinite behavior happens when the infinite behavior happens, the infinite next gadget, okay. So we need to dive into the infinitely many next argument. So in this case, M is first evaluated to the next M1, and next M1 is evaluated. And the evaluation of M1 is evaluated to the next M2, and then M2 is evaluated, and so on. Then, by assuming that the rate operation is applied to the next infinite effect of the next argument M, then if this program is diverges, every informations about the infinite behavior must be accumulated. I see. Right. Yeah, sorry, and then, yes, and actually we assume that there are some finite effect, there is some finite effect that accommodate all the finite actual traces. Yeah. Right. So we assume that some limit exists in a sense.
Okay, we're at the end of the session, so let's thank Taro and take our next questions to the coffee break.
Okay, welcome to Quantum 2. My name is Jens Paulsberg. I'll be your session chair, and we have two wonderful papers. The first paper is on automatic uncomputation, and the speaker is Kengo Hirata.
Right, thank you for the introduction. So this is a paper about quantum computation. So let me review about the difference between the classical computation and quantum computation first. So in quantum programming languages, the data we use are different from usual classical computation. So first of all, in classical computation, we use sequence of bits as a data, which is just this, 1 or 2 data. And on the other hand, in quantum computation, we use qubits, which is just a linear combination of these bits. And for functions, programs, we can do like usual arithmetic function in classical computation, but in quantum computation, we have two basic operations you can do, which is unitary operation and measurements. So unitary operations are kind of usual computation, and measurement is a kind of projection from the linear combination to one sequence of bits. And for the type system, in usual classical computation, you can do anything, but like including copying resources or discard resources. But the main difference between classical 1 and quantum 1 are that in quantum, you cannot copy or discard, and it's called linear type. So let me look into this linear type in detail a little bit more. So in linear types, you cannot copy or discard. So the copy means, prohibiting copying means you cannot write the program at the top, which uses this x twice in the first line and in the second line, which corresponds to non-calling theory in quantum computation. And prohibition of discarding corresponds to prohibit a program which looks like at the bottom, which implicitly forgets this resource y, which corresponds to principle of implicit measurement. When you forget something in programming language, then that corresponds to implicit measurement. But we don't want to do measurement implicitly because it's kind of like a factorial operation. You don't want it to do it implicitly. So that's the point of linear types. But the problem is this prohibition of discarding is sometimes a little bit not very convenient. We sometimes want to allow kind of discarding. So let me explain what kind of thing happen in quantum computation. So the example I'm going to consider now is like this. And so we're given a built-in function and, which takes 3 qubits and outputs 3 qubits. And we don't do anything on the first 2 qubits, but we compute Q3 XOR Q1 and Q2. So if the input was 0, 0, 0, and then the output is going to be 0, 0, 0. But if the input was 1, 1, 0, then the output is going to be 1, 1, 1. And so this is the given function you can use. And the goal you have to do is to make a function, and3, which takes 3 qubits and outputs 4 qubits, which computes Q1 and Q2 and Q3. So for example, if the input was 1, 1, 1, then you want to compute 1, 1, 1, 1. So how to make this program? So this is the example implementation. And this takes 3 qubits, which has, So we have qubit types, and it takes 3 qubits and outputs 4 qubits. And what we have to do first is to introduce a temporal value, which is initialized by 0. And then apply AND to compute x and y. Next, in the next line, we introduce another qubit, which is going to be the return value, and compute x and y and z. So now we got x1, y, and z, and we still have x1, y, and z. So is the computation done? No, because we still have the temporal value, which has to be discarded. But you cannot measure this, so you have to reset this x and y in some way. So how to do that? To do this, one way to do this is to apply AND again here. And after applying this AND, so you get x and y XOR x and y, which is 0. now you got 0, and this 0 doesn't have any information like x or y, z, so you can safely measure this and turn this ket 0 to classical bit 0, and then it becomes a classical confirmation. And because classical information can be discarded at any point, so now, oh, sorry. Oops. Oops. Yeah, so you can now discard it, and you get the computation. So it's done. So this is how we implement this AND3 in linear type. But is this we actually want to do? Like, no, it's not like we don't have to measure this, because this measurement doesn't do anything. We just need to know that temporal value is reset to 0 here. And then we just wanted to just forget the allocation. We want to deallocate this temporal value. But now, this now violates the linear types, and we now have the verification problem here. So that's why we don't want to have like strict linear type in this concept. But what about this third line? This third line was only introduced to reset the temporal value, and the actual computation was only the first 2 lines. So let's say we also don't want to write this, but we expect the compiler to do this automatically. So that kind of system is called automatic uncomputation. So in a language which has automatic uncomputation, you only need to write first 2 lines and then forget this temp and expect the compiler to detect this forgotten temp and then reset it to 0 automatically. So let me summarize the concept of automatic uncomputation. So uncomputation is a way to drop resources in a safe way, in some way, yeah. And automatic computation is what does automatic uncomputation does is first detect the drop the batteries and verify whether you can actually reset it. And then if the compiler knows how to reset it, then we expect the compiler to do it. So we're now interested in what kind of verification we have to do here. So what do we have to do is mainly we have 2 points. First one is that because when we want to reset this temp, we actually need to use x and y again. So first point is that we have to have x and y still alive and unchanged when we want to drop this temp. So that's the first point. And the second point is that unfortunately, not every computation can be uncomputed, so we have to have some kind of restriction. And one of the sufficient restrictions is to know what you have done to this temp is almost like Boolean circuit, which is classical computation. But this sounds like a strict restriction, but it's a kind of reasonable restriction. Right, so this is something we want to do in verification. And to make a type system for this automatic computation, what we want to do is to introduce a special type, sharp D, which means that you can drop something. But I mean, it has to be essentially linear, but in some way you can drop this. And what we expect in the type system is that we want to implement this AND prime, which takes 2 qubits and returns another qubit, which is droppable. And in this type system, this sharp D has to be like a little bit weaker than linear type because it's allowed to drop. It's allowed to be dropped. But it has to be stronger than affine types because it can be dropped only until x and y changes. You cannot drop it unrestrictedly. So that's the point we want to do. And so here, we notice that we have to have the kind of notional time in our type system because we need to know the x and y until x and y change part. And we also have to know that unchanged thing in type system. So how to do that? The solution we found is to use the type system in Rust and lifetimes. So lifetimes are just kind of interval of program, time of interval, and it forms a posit. And with this lifetimes, we can make so in our type system, we introduced 2 special types. which is droppable sharp alpha, which means droppable until alpha. And we also need to have immutable reference, which means you can it stays unchanged until some lifetime alpha. And now, what we want to have is the function n prime, which takes two immutable qubits and immutable references and outputs one droppable reference, droppable qubit. And it has to have common lifetime because you need to match this time. So that's the idea. And with this lifetime annotated sharp type, this lies in between affine type and linear types. And if this alpha is the kind of longest one, which means that you can drop at any point, then it matches with the usual affine type. On the other hand, if the alpha is the kind of shortest one, which means it's already happened, in that case, this sharp alpha t means that you can never drop, which is going to be the same as linear types. So that's the idea of our type system. And what we have found out is that automatic computation can be nicely represented by Rust and combining with basic quantum types and affine types with lifetime sharp alpha t. So, and we only explain a very easy example, but in general, we can the temporal value we want to drop can depend on a lot of other variables which has different lifetimes, but we found out that lifetimes can completely characterize the droppable thing. We also gave two operational semantics in our paper. And the first one is something we call simulation semantics, which is a kind of naive semantics of our language. But the problem is that this doesn't give you how to compile a program. For example, like this program, forget, takes 1 qubit, but immediately forget it. But so this means uncomputation, but the uncomputation depends on what kind of computation you have done on this X. So this forget function doesn't compile to a unique circuit. So that's the first simulation semantics. And the reason I call this simulation semantics is that you cannot represent it as a circuit, but you can represent it in a mathematical way, and you can simulate it in CPU easily. On the other hand, we also gave another semantics, which we call uncomputation semantics. And in this semantics, we interpret a program into a circuit graph, which is a kind of directed graph, which preserves all the history of the computation. And then in this directed graph, you can play a pebble game, which is a kind of game you can put a pebble on a node or take it out. And putting a pebble corresponds to do a computation, and taking it off is correspond to uncomputation. And we found out that any strategy on pebble games give you actual computation. And we also proved that these two semantics are equivalent in some sense. So that's the point. That's the two semantics we gave. And we also want to talk about the related work. So the automatic computation governed by type system was firstly introduced by Silk, which is pretty nice work, which also has a CPU simulator, which we don't have it yet. But the type system was kind of ad hoc and was a little bit tricky. But in our work, we found out that the type system can be represented very nicely with adding sharp alpha t to Rust type system. So we also have lifetimes, which not only can be used to verify the uncomputability, but it can also be used to optimize the uncomputation. We also can have forget function, but this function doesn't type check in Silk. So that's the difference. So as a summary, we introduced a new type system for automatic uncomputation, which uses type system Rust and add a special type sharp alpha t, which is a fine type, but restricted by lifetimes. We also give a lot of examples, and we also give two semantics. And we prove the equivalence of two semantics. And the interesting point of the second semantic is that we use Pebble games as a backend, which has been studied as a model of uncomputation, but like it was not like studied as a part related to the relation between the programming language was not made clear. So as far as we know, this is the first language which uses Pebble games as a backend of our semantics. So that's the end of my talks. I would glad to have some questions.
Okay, questions. We'll bring a microphone to you. Just raise your hand. First question over here.
Hi, thanks for the very cool talk. You mentioned that it's possible to automatically uncompute values that have been computed by classical computation.
Yeah.
In general, it's also possible to do this if you've applied phases like Z gates or RZ gates. You know, it's also safe to do those. Does your system account for such a generalization, or do you see any challenges?
Well, for example, like a simple counterexample is like if you add automart gate, then I mean, I have to do some mathematics to explain this, but automart gate, I mean, that's kind of very simple, like basic operation and quantum computation, but automart gate, it's prohibited in quantum of this automatic computation. But probably, yes, I'm thinking of like extending how to like, you mentioned like Y gate. No, rotation gate.
In this case, you probably Z gates or RZ
Yeah,
gates would be fairly easy to support.
I mean, that's kind of future work. Yes, it hasn't been considered in our work, but that's a nice future work, I think.
Thank you.
Other questions? Over here.
It's a question by a non-specialist. Huh? So you say you can do this when you want or never. But there are many other possibilities in between. And why don't you use some temporal logic to express you cannot do it until you do something, and then if you do it before something happened, then it's okay, but afterward you cannot, or things like that. But temporal logic will allow you to express these properties. Would it be interesting?
Yeah, I think it's gonna be interesting. But the reason we use Rust is that we also need to have like the immutable reference, which is already built in it's already a part of Rust, and we found out like lifetimes can be fit very nicely with this. But probably there are a lot of other way to do like represent. You have to do something before something happens. I think that's, yeah, it's possible. I think it's possible to do in another way. Thank you.
Question over here.
Hello. I have a question about, so I imagine you prove some kind of notion of type safety, right? So that your type system, it preserves the semantics in a certain way. And I imagine you're taking like a syntactic approach here to prove type safety, like usually by progression preservation. And if in this, if you take a semantic approach, how would you go? I would imagine that's a bit hard to prove that when you have a substructural type system, such as yours, which is, I think it's substructural, right? And if you have references, I thought like it's quite hard to prove this in a syntactic way, type soundness. Like maybe you can say a bit more about how you, is there something to say about type soundness here?
Type sound, I mean, we have subtyping. What do you mean?
I mean, like proving that your type system is, obeys the semantics.
Yeah.
Like type safety, I mean.
Can I give an attempt at rephrasing?
Yeah, sure.
So I think he's asking, you have the type system, and we want a theorem about the type system that says that it's sound with respect to one of your two semantics.
Right. Yes.
Do you have this in the paper already, or is it?
I'm not very sure how to represent it, but like, I mean, it's not very functional. Then it's like it just like do one thing and one thing in each step, and type is preserved in some in those steps, but if you want to change the types, you have to. We have like a type coercion, which is because we have like subtyping, so you can do that. But you cannot do it implicitly in our theoretical paper, but I expect to have that in the implementation. We don't want to write every type coercion explicitly in implementation, right?
I imagine it's some kind of progress preservation, but we can talk about it afterwards.
Yeah, thank you.
Yeah, definitely. Let's do that. One more question. Anyone wants to ask the last question of this part? Let me ask you, what's the largest example you have shown that type checks?
We did the Grover.
Okay.
Yeah, Grover algorithm.
Very good.
That's the largest one, I guess.
Excellent. All right. Thank you again.
Thank you.
Okay, we are moving on to the second talk of the session. Let's set up a little bit here. Okay, so, the second paper is about verification, and the speaker is Fangyi Lo.
Hello, can you hear me? Okay, so hi, I'm Fangyi, and I'm the presenter today. And I'm going to talk about how we define a new automata to efficiently verify quantum circuits. And for the outline, we will start from a quantum state and its representation, and then introduce AutoQ, our framework, and then the new defined level synchronized tree automata, LSTA, and conclude with the summary and some future directions. And it's really similar to the previous talk. So in quantum computing, the basic unit is a qubit. And a qubit can be 0 and 1 at the same time. So we usually represent a quantum state as a linear combination of the classical 0 and 1. And below are two common representations for quantum states. For the vector representation, a quantum state is expressed by a column vector. And for the tree representation, as you can see, the left node is correspond to the state 0, and the right node is correspond to the state 1. So now, if there are 2 qubits in your system, so there will be 4 possible classical states, and a quantum state can be all 4 of them at the same time. So as you can see, the length of the vectors doubles, and you need an additional level for tree representation. So now, if there are n qubits in your system, a quantum state actually encodes 2 to the power of n, that is exponentially many classical states simultaneously. So that is the reason why quantum computing is potentially faster or more powerful than classical computing. And for the following slides, we will use tree representation. Now let me introduce AutoQ, our framework, a Hall-style automata-based quantum verification framework. So as usual, a Hall triple consists of a precondition, a quantum circuit that we want to verify, and a post-condition. And in AutoQ, the pre-post conditions are sets of quantum states. And a quantum circuit is a series of quantum gates. And so executing the quantum circuit is sequentially apply the quantum gate to corresponding qubits. And there may be a quantum gate that apply to multiple qubits at the same time. So in AutoQ, a Hall triple is valid if for every content state in the precondition. After executing, the circuit reaches some state in the postcondition. So now you may wonder why we choose a set of quantum states as our pre-post conditions. So the intuition here is a quantum state is a linear map. So you can verify a quantum circuit by sending a basis of the domain X under it and examine the result. So you can check that if this quantum circuit is actually correspond to a certain linear map. And since a normalized basis is a set of unit length vectors, so it's actually a set of quantum states. Oh, so this is the intuition. So the next question is, how do we encode a set of quantum states? Recall that in automata theory, an automaton recognizes a set of strings. So here our goal is to encode a set of quantum states in tree representation, that is a set of tree. A set of trees. So we can actually use a tree. We can actually use tree automata to encode sets of quantum states. That is, given a set of quantum states that we want to encode, we want to construct an automaton A such that the language recognized by this automaton is equals to this set of quantum states. Next, we want to calculate the set of quantum states after executing the circuit. So since executing the quantum circuit is actually sequentially apply all of the quantum gates, we design algorithm for all common quantum gates. So that given an tree automaton A as input, the algorithm will try to construct a new tree automaton gate of A such that this automaton gate of A actually accepts all the quantum state after applying the corresponding quantum gate operation. And for the complexity, the size of the automata increase quadratic or constant to the size of the input automata. And this is for all of the quantum gates except Hadamard. And for Hadamard, it will be exponential, and we will talk about Hadamard gate later. And for the last step, to verify a whole triple, we want to make sure that for every quantum state in the precondition reaches some state after executing the circuit. So this is actually equivalent to check that the set of quantum state is to check if the quantum state set of quantum state after executing a circuit is a subset of the post condition. And since here we use automata to encode sets of quantum states, so those sets are equivalent to the languages recognized by some automata. So that is, to verify a whole triple in our framework, it actually reduced to the language inclusion check of tree automata. So overall, as long as we can use tree automata to encode our pre-post condition, and since we design all the algorithm for all the quantum gates, and with the help of language inclusion check of tree automata, our framework AutoQ is fully automated. So I mentioned earlier that the complexity of Hadamard gate is exponential. And this is really bad because Hadamard gate actually occurs frequently in our benchmarks, and sometimes over 90% in some cases. And I will show you that the solution to this problem is our new defined level synchronized tree automata, LSTA. So first, we're going to talk about what does the Hadamard gate do to a quantum state and why is it difficult for a tree automata to handle it. So given an input quantum state as the tree on the left-hand side, after we apply Hadamard gate on the first qubit, the output quantum state will be the tree on the right-hand side. And where you can see that the left subtree here, the left subtree of the output combines the sum of the left and right subtree from the input. And similarly, the right subtree of the output represents the difference of the left and right input subtrees. So that is, for this node A, when we try to calculate the result of after applying head gate, node C needs some information from, node A needs some information from node C. So in a sense, what we want to try to build a connection between nodes so that we can calculate the result after applying head gate efficiently. Now, however, in automaton level, that means you try to synchronize between node A and node C. And so one way to, or maybe the only way to do this is you try to propagate the information of node A through the transition and state of automaton. So you can imagine that you actually try to pass the information of A through this path. And the bad news is there are exponentially many different branches need to be synchronized as the levels of tree increase. So this is the reason why standard tree automata are inefficient to use for handling the head gate. So right now we kind of want a tree automata that can synchronize between different branches efficiently. So since there isn't one, we define it ourselves. So let me introduce once again our level synchronized tree automata, LSTA. And the biggest difference between standard TA and LSTA is consider that this is a non-deterministic top-down tree automata. So there might be some state queue that have multiple outgoing transition. But in LSTA, you have to label those transitions with disjoint choices. Also, for an accepting run of LSTA, we have this further restriction that if different branches start from the same state at the same level, they must make the same choice. So I will demonstrate this idea with this partial run. And as you can see, both the left and right node are at the same state. So there will be 4 possible following run for this partial run. And since we have the restriction that different branches start from the same state at the same level must make the same choice. So these 2 partial runs are actually illegal. And as you can see, the result is we perfectly synchronize different branches for every single run. So I won't go into detail, but with the help of LSTA, we essentially improve the complexity of head gate from exponential to quadratic. And here is the verification time comparison between standard TA and LSTA. And the difference is obvious. As you can see, for some cases that is timeout for standard TA, LSTA verify the circuits within a second. And we can also, for the 4th row, we can also verify some interesting properties that after executing one iteration of Grover's circuit, the probability that you get the correct answer increase and up to 200 qubits and within 18 seconds. And you can find more benchmarks results and some comparisons with other state-of-the-art verification tools in our paper. So here I list some key properties of LSTA. So it is closed under union and intersection, not closed under complement. And the emptiness is p-space complete. And we designed the algorithm for language inclusion check. And the problem itself is P-space hard and in EXP space. And for the succinctness, there exists some set of tree such that you can express it in linear size of LSTM, but you must use exponential size in the tree automata. And finally, maybe the most important one, LSTA is, the expressiveness of LSTA is actually incomparable to TA. And you can find all the detailed proofs and the algorithm in our paper. So for the takeaways, we propose a whole-style quantum verification framework and using sets of quantum states as pre-post condition, and using tree automata to encode set of quantum states with providing the algorithm for gate operation and the inclusion check for a language inclusion check of tree automata. Our framework is fully automated. And we also introduce LSTA to efficiently handle the frequently occurring Hedmark gate in quantum circuits. More specific, we improve the complexity of the algorithm from exponential to quadratic. And the last point, LSTA is incomparable to TA, and the emptiness and the language inclusion check for LSTA are decidable. The intersection of automata and quantum is a fruitful area of research. And while we continue to enhance the capabilities of AutoQ, our focus extends to a variety of exciting projects. And for instance, we are exploring the use of automata to verify Hamiltonian simulation, a significant application in the field of physics. And also, we try to use automata to automate other verification frameworks, such as quantum Hall logic. And this is me, and I'm a research assistant from Taiwan, and I'm looking for a PhD position, and I'm ready for a QA, and thanks for your listening.
All right. Questions? Please, over here.
Well, thank you for great talk. I'm wondering whether can we support intermediate measurement in your framework, because some are promising quantum applications in future, like fault-tolerant quantum computing. Such intermediate measurement is an essential tool to implement quantum algorithms in a fault-tolerant way. How about it?
Do you mean can we support measurement in our framework?
Yes.
Yeah, and let me expand on his question a little bit. Can you support measurement in the middle of the circuit, or can you only support measurement at the end of the circuit, or not at all?
Yes.
Okay.
We do have an extension for that, but it's an ongoing project. Yeah.
So not in the paper?
Yeah.
Okay.
Very
good.
Okay. Yeah.
So I hear from the co-author over here that there's already a paper accepted in TACAS, I understand, that has some of this stuff in it that you're asking for. All right, other questions? Over here.
In our logic, you have two kinds. One that partial correctness or non-terminating execution are ignored, and the one which is total correctness, where you prove there are no infinite executions. So I think you use partial correctness. That is, you assume that execution terminate or not. So I have a related question, which is your tree seems to be regular tree. And so they are built out of finitely many patterns. And if it does not terminate, you might have infinitely many patterns. So I have the impression that it only works if it terminates. Sure.
So do you mean that if there's a loop in the tree automata, right? So actually, here, we do try to use tree automata to construct like parameterized circuit, so we can verify the circuit for n qubit and n for the natural number. But it's also an ongoing project.
Okay, I think people are hitting on some good points here. Another question, please? Let me ask you a question. For Grover's algorithm, you had different measurements. What is the property you are verifying for Grover's algorithm?
Oh, so for this one, the precondition is only single quantum state. So it will be like so the amplitude for the correct answer will be V high, and the other will be V low. And we tried, and after executing the circuit, the new amplitude correspond to the correct answer should be like V high prime, and we want to make sure that V high prime is greater than V.
I see. And you can specify that in your framework?
Yes.
Oh, very good. Okay. Who wants to ask the last question of the session? I don't see any questions. Okay. Thank you again.
Thank you.
Let me say, remember that there's a SIG plan meeting coming up at 6. Okay, Claire.
should start. Guess we should probably start. I don't know of a reason to wait, or should we give people another minute? So we're right on, amazingly.
People are going to already here. I guess a couple of people are just walking.
Trickling in. We'll give them another minute. Could go. I could go clap in the hallway or something. I guess we're ready to start. All right. All right, everyone, we're about ready to start the business meeting. If you could take your seats. We're about ready to start. Could you please take your seats? We'll get going. All right, we have pretty packed agenda for this evening. Welcome to the business meeting. We have the chair's reports, an award ceremony, and then some announcements and updates, followed by a general discussion. So let me first thank you all again for participating in POPL and making it quite an eventful week. It's been memorable in lots of ways, I hope. So let me begin with my chair's report. So I shared most of this, or much of this, on the welcome yesterday, but this is just a reminder of the packed event schedule that we have been experiencing. We're almost to the end. We have Friday and Saturday events still to come. But this year, like many past POPLs, we have had quite a rich array of things to participate in. So I hope this has made your week quite exciting. I want to particularly thank our industrial sponsors. They've been quite generous in their sponsorship of the events. And as you can see, we raised a total of approximately $96,000 to help support this amazing conference. I thought I would give you a little bit of context about costs and pricing. That's been a question from previous years. So this highlights the registration rates of recent POPL conferences. So you can see, we've been trying our best to keep the registration rates as low as possible or reasonable as possible. This is, as you'll see in a minute, the registration rates basically boil down to a combination of location and venue. And of course, whether it's in the US or Europe makes a big difference. So this year, our kind of standard ACM member 3-day POPL registration was $800. And for students, we give a significant discount, $475. Those are sort of the baselines. There's a whole table that you can find on the website. If you have early bird registration, you get a discount. If you are not an ACM member, you get a slightly higher fee. And then, of course, there's the workshops, which you can buy on a per-day basis. And of course, we also have virtual participation tickets, those are basically a fixed rate, $75 for the entire week or $50 for early registration. So we tried to keep things on par with previous years. I can summarize attendance and venue trends. So you can see this is the sort of history of recent POPLs. Room rate and location are, of course, one of the components of the cost to travel to a place and to participate in the conference. And of course, where we have POPL affects the number of attendees. Denver, as you might expect, is, well, we knew that it would be a smaller attendance because it's not located in a population center as it's not as densely populated here as in the East Coast or, say, London. And so we can see the effects of that this year. But nevertheless, 560 plus attendees for this year is quite strong, I would say. That number is has an asterisk because it's a little bit out of date. We haven't yet incorporated on-site registrations and sort of last-minute participants. I guess it's most comparable to the last time it was held, not on the East Coast or Europe, which was in LA back in 2018. It had about 586 participants. So to me, this basically says that we're getting healthy participation. To kind of give you the financial picture, if we take that $96,000 supplied by the donors, we use the rest of we calculate the ticket prices based on expected participation rates and hotel venue, et cetera. This table gives a summary of sort of the brief summary of the expenses for the conference. As you might expect, the biggest charges are the catering and the food. That tends to be the most costly piece of any event like this. The equipment, room, AV is also quite expensive. And then there's a bunch of miscellaneous things that add up to quite a large chunk of change. The ACM charges an overhead, but that provides benefits for things like insurance in case there happen to be unusual incidents at the hotel. So I think we haven't yet sorted out the consequences of any of that. I'll be filing an incident report with the ACM about the circumstances of the hotel here, and that is still playing out. I guess the TLDR on this is that for this year, as is the hope, POPL should basically break even, and we're doing great financially. So, so that's sort of the summary of the sort of logistical things, finances, and so on. For the rest of my spiel, I just really wanted to re-thank the people that I thanked yesterday, because this year, I think in particular, has been remarkably challenging to organize behind the scenes. We had a large chunk of the student volunteers and AV team and the conference organizers and the hotel staff basically working entirely through the night on Tuesday to make sure that things could run as smoothly as they could. I kind of think of it as a minor miracle that we didn't have to really change the schedule more than we did. And so all of these people deserve a huge amount of thanks. Of course, yes. Especially the AV team. And especially the student volunteers. So I also did want to shout out again the UC Boulder folks who were very instrumental in helping us get the AV equipment here to begin with, and my personal gratitude to all of the people involved. It has been really a testimony to the heroic efforts of this team that have made this the success that it is. So thank you all. And with that, I'm going to turn it over to Armando to give the PC Chairs report.
Thank you. Yeah, so I hope all of you have been enjoying the program so far. There's still one more day of exciting papers and presentations. So I want to talk a little bit about how it came about. So first, some statistics. So we had 298 submitted papers, which is more or less on trend from previous years, except for last year's somewhat of an outlier, larger set of papers. And the acceptance rate was also very much in line with what has happened in the past. We had 26.5% acceptance rate. Now, if you're interested in also how the statistics break down by different areas, I don't know how well you can see the captions at the bottom, especially from behind. But the most popular areas are verification, program analysis, type systems, inference theory, functional languages, semantic models, program logics. And these categories, and one of the things that to me was surprising is the ordering of these different areas has been remarkably stable over the years. If you look actually at the top 10 areas for submissions, you can see that they're pretty much the same from years before. One of the things that to me was surprising and a little bit sad was that program synthesis dropped from the top 10. But probabilistic programming is in, so that's cool too. But I mean, all of these areas are fun and exciting, and it's nice to see a lot of exciting work here. If you're interested also on the acceptance rate by different areas, in general, it's relatively uniform, except if you're submitting machine learning papers to POPL, maybe no, but it's you know, there's room for machine learning here even at POPL. But yeah, I'll give you a second to digest the graph. On the other hand, decision procedures and proof assistants seem to do pretty well. Now, a little bit about the decision process. So we had a single flat PC with 76 members. We ended up with around 10 to 13 papers reviews per PC member. And as has been the case in recent years, we had a set of associate chairs. We had 5 associate chairs this year. And each of the associate chairs oversaw around 60 papers. And I want to say that the associate chairs are really the heroes of this story, and I really want to acknowledge them. These are our 5 associate chairs, and they were the ones who were really on the trenches, going and participating in every single paper discussion and making sure that that everything was on track. As in last year, we had a full double-blind review process. It means that the author identities are only revealed at the point of conditional acceptance. So papers that are turned down preserve the anonymity so that when they get submitted in the future, the reviewers still don't know who the authors are and can potentially review those papers again without being affected by knowing who the authors are. And one of the things that was also introduced last year that was preserved is that program committee submissions are treated the same as any other submissions. So we're doing away with the higher standard that was in place that was in place before. And happy to talk more about that. Now, the reviewing process. So papers were assigned 3 initial reviewers based on bidding in HotCrap. This is similar to last year's. And one of the things that we did this year was that the reviewers were actually due 3 weeks before the start of the rebuttal period. And during these 3 weeks, the idea was to, on the one hand, allow for initial discussions and to especially to identify papers that might need additional expertise. And we ended up recruiting additional reviewers for 58 papers. And this included 3 papers that got an expert review after the rebuttal period. And the focus for these additional reviews was some papers with divergent scores and insufficient expertise. So we really wanted to focus on papers where there was a strong interest from some reviewer for the paper, but also there was not enough expertise to really make a decision on it. So now, when it came to actually making decisions for the papers, so we wanted every accepted paper to have an explicit champion for the paper. But one of the things that is challenging when you have a remote program committee, when you don't have a program committee meeting, is you tend to have 2 kinds of, I hesitate to use the term borderline papers, but 2 kinds of papers where it's difficult to make a decision. One kind of paper is where you have active disagreement between the reviewers. You have one reviewer that says, this paper is awesome, it absolutely has to get in, and you have another reviewer saying, I don't know, I don't like this paper, it has this and this and this shortcoming. And so, but you also have other papers where all the reviewers roughly agree on the level of this paper. They are just not sure whether it's above the bar or below the bar. And one of the things that is very important is calibration, right? You want to make sure that you're applying a consistent standard across the papers. So for the papers where there was active disagreement, we told reviewers from the very beginning that we would have Zoom meetings for individual papers to resolve those disagreements. In the end, we actually didn't have to do Zoom meetings for any of the papers. A lot of the papers where there was initial active disagreement were helped by bringing in additional expert reviewers who ended up shifting the discussion in many cases and leading to convergence. But for the calibration cases, right, it's important to have a uniform standard, and it's especially difficult because every individual PC member really only gets to see about 4% of the submitted papers. So it's hard to apply a consistent standard when everybody has only a very narrow view of the full pool of papers. So this is where the associate chairs were really critical in ensuring that a consistent standard was applied, because every associate chair has much broader visibility over a much larger set of papers. So we actually had a calibration meeting with the associate chairs, where each associate chair brought into the meeting 3 papers that where there were calibration questions, where roughly the reviewers agreed on the qualities and issues with the paper, but they were not sure if it was above the bar or below the bar. And so we discussed each one of these papers all together as a group to make a decision both about the individual paper, but also about the criteria that was being applied, so that then the ACs could go back to some of those discussions that hadn't converged yet, and nudge some of these decisions to aim for consistency. Now, I use the word nudge here very purposefully in that, at the end of the day, the reviewers are the ones who have the final word over whether the paper gets accepted or rejected. And there were a few instances where the conversation was going in a certain direction, and the AC would say, okay, this paper looks like there's not enough enthusiasm for it, especially relative to other papers that we have accepted. And one of the reviewers that maybe had not been as active in the discussion would use this as a nudge to jump in and say, no, actually, this is a really good paper, and I really want to champion it. So at the end of the day, it's really the reviewers of the paper who have the final say. So big thanks to the associate chairs. But also, of course, big thanks to the program committee. One of the things that is very particular about the timeline for POPL is that it very much intersects with people's summer break plans, and so a lot of the people in this list, and here's more program committee. A lot of the people in this list really had to take piles of papers with them to their summer break, and it's a big thanks to everybody who at the end of the day made the exciting program that we have here possible. And finally, some special thanks to everybody who participated in making these possible, especially the organizing committee led by Steve, the artifact evaluation committee led by Caleb and Vadim, the conference publishing team with Dirk and Simone, who always do a great job helping actually take the process from submitted camera-ready versions to actually having papers published. And I really want to thank especially the previous PC chairs, especially Amal and Derek, who were extremely helpful. I think Derek in particular, I would send him emails at random times of the day or night, and he would just seem to respond within minutes. And thank you. And now I want to switch gears and start with the awards part of the program tonight. So we have seven distinguished papers that we want to recognize today. And so the way we're going to do this is we have some certificates for the authors. So I'm going to mention the papers and call on the authors one by one. And if you can, please just come here. We'll give you your certificate and stay around so we can take a final group photo at the end. And so we're going to start with the first award. So this is for the paper Guaranteed Bounds on Posterior Distributions of Discrete Probabilistic Programs with Loops by Fabian Sazier, Andrzej Murawski, and C.H. Luke Ong. So please, if you can come to receive your certificate. So the next paper is Relaxed Memory Consistency Re-Executed by Evgeny Moisenko, Matteo Melusi, Innocenti Meleshenko, Ivan Kabashny, Shoam Chakraborty. And unfortunately, none of the authors of this paper could make it in person today because of visa issues. But we should still clap for them. The next paper is TensorWrite, automata verification of tensor graph rewrites. And the authors, please bear with me while I butcher lots of names. Sorry about that. Jai Arora, Cyril Liu, Devanash Jain, Tianfan Xu, Farsin Hushmand, Pichai Mangpo Tolimantha, Mohsen Lesani, Praveen Narayanan, Karthik Srinivasan Murthy, Rastislav Bodik, Amit Sabne, and Charith Mendis. The next paper is Barnjert Convenis with Naster and Tarski. Strong rule induction for syntax with bindings. And the authors are Jan van Bruch, James McKenna, and Andrei Popescu. The next one is Affect, an affine type and effect system by Orpheus van Rusch and Robert Kravers. The next one is Data Race Freedom a la mode. Aina Lin, Benjamin Peters, Layla Elberhani, Leo White, Stephen Dolan, Richard A. Eisenberg, Chris Casingino, Francois Potier, and Derek Dreyer. And last but not least, a primal dual perspective on program verification algorithms by Takeshi Tsukada, Hiroshi Uno, Odette Padon, and Sharon Shoam. And so now if you can all come here, I guess we can come up to the podium for the group award picture. I think we can fit all of us here. All right, and let's thank everyone. And congratulations. And now Alexandra is going to tell us who is the most influential POPL paper.
Okay, thank you, Armando. So I get the pleasure to announce the next award. So on behalf of the SIGPlan EC, Nick Vazu and myself run a bunch of SIGPlan-wide awards, which include the most influential awards for each conference. And this award is given to a paper that was presented N-10 years ago, so 2015. And you can look on the website. There's a committee that convenes the PC chairs of those years and the general chair, and also the PC chair and general chair of the previous year, and some SIGPlan representatives. And the paper chosen as the most influential paper for 2015 is IRIS, Monoids and Invariants as an Orthogonal Basis for Concurrent Reasoning. And so this paper was selected by the committee for a very long reason. I have a sort of shorter version. So this paper introduced IRIS, which is a unifying framework for higher order concurrent separation logic, mechanized in Coq. And at the time IRIS came along, the field of separation logic had become fractured, with many different and potentially incompatible logics being developed with bespoke models. The first paper on IRIS showed how a few key ingredients from prior work could be fruitfully combined to derive sophisticated proof techniques that were then built in as primitive in prior logics. This was just the first step in a long line of work that generated a very rich and diverse community. So thanks to follow-up work on IRIS proof mode in ROC, IRIS has become a widely used tool in program verification and programming language method theory with many applications that are listed here, and I'm sure many of you in the audience know. So without further ado, let me call the authors to come and receive their award. Let's give them a big applause.
I get all of them.
Okay, who wants to start?
Thank you very much. Thank you very much. We are, of course, very happy and very honored to receive this award. I would like to say a few words, and I would like to stress that IRIS was, of course, not developed in a vacuum. It was built directly on the top of a rich body of prior work, without which it wouldn't have been possible to do it. Especially, there was a lot of work on logical relations and high-order separation logic. It only became successful thanks to a rich body of work that came after it. Maybe I can also mention that it was not at all clear to us when we started the work on IRIS that it would amount to much. The original draft that we wrote was really quite rough, and I also recall telling my students that it was maybe not so clear to us that it would have a good chance of being accepted at the conference. And indeed, the reviewers also found that the paper was quite rough. It received a whole rainbow of reviews, A, B, C, D. So this was probably the very definition of a borderline paper. I think we were quite lucky to have an expert reviewer who liked the paper. I think the rest of the reviewers were not really convinced. Maybe this doesn't mean that we should accept all papers that one person likes, but maybe it's good to remind all of us, myself included, that it's good to be humble about how we evaluate, the significance of new work. Maybe I'll turn over to Ralph.
Yes, let me also start by expressing my deepest gratitude for receiving this award. This is a great honor. As Lars already mentioned, I want to emphasize that the IRIS paper that receives this award is only the starting point of a long line of work by many authors, and we would not be standing here today if it were not for all these people that helped improve IRIS over the last 10 years. One of the best decisions we made early on in Iris was to manage it like a collaborative open source project with public issue tracking and merge requests and all of these things, together with an open chat room, which we called the help desk, which at this point has over 300 people in it. And at this point, a series of 4 workshops, which altogether helped build a vibrant community around Iris that both helps maintain our shared artifact, the library, but also helps point newcomers in new direction and get people started with this framework. I want to particularly call out one person who really ought to share this award with us, and that is Robert Kravers. Robert is the main architect of the ROC mechanization of Iris, and most importantly, he's the implementer of the Iris proof mode. Being able to carry out separation logic proofs inside the logic in a proof assistant is one of the key ingredients of Iris, and I'm sure the vast majority of Iris-based projects would not have been mechanized if it weren't for the Iris proof mode, and likely they wouldn't have picked Iris at all. So with Robert, without you, Robert, there wouldn't be Iris. So all of this goes to say that the success of Iris is in large part a reflection of the inspiring and collaborative nature of the PL research community, and we want to thank all of the Iris contributors who have helped develop and maintain Iris. This award goes to all of you.
Thank you all. So I won't keep you very long. I just want to say, first of all, I'm deeply honored by this award, like my co-authors, and thankful for our vibrant PL community that made the success of Iris possible. I just want to say a few words about how Iris originated, which I think you might find interesting. So in early 2013, Muli Sagiv he approached me and Lars, actually, to ask if we would write a monograph, a pedagogical text for teaching people about reasoning techniques for higher order imperative programs. And we both thought this was a great idea. We were very excited. We quickly got to work on creating a Git repo, which we called NowBook, because that was named after the Muli's publisher was Now NOW Publishing. We thought we'd start working on it now. But you can guess what happened. About 6 months later, maybe it was 9 months later, I don't remember. We had still made 0 commits to this repository. Okay. And that was, it actually became a running joke because we started calling it the later book. It's a step indexing joke if you don't get that. Anyway, the reason we were stuck was that we were missing something essential. We did not have a logic that was simple and expressive enough to serve as a foundation for teaching students. And filling that gap is what eventually led to Iris. And so this brings me to my conclusion, which is just, I know we're all focused on doing new and exciting research that pushes the boundaries of knowledge, and that's fantastic. That's why I come to POPL every year. I'm always excited to come to POPL and hear about that work. But I do think from time to time it's nice to step back, get some perspective, and try to build things that are just useful according to whatever metric you personally care about. Even if it's not easy to convince the POPL PC that they're novel enough, and even if you get review scores like A, B, C, D. And so I think this is a good, and I think Iris is a good and hopefully an encouraging example of that. Thank you.
Please don't forget all the many. Okay, so thank you very much. And now I will hand over to Rolf again and Neil to talk about the SRC. I thought you could run away.
Yes, no escape from this. Yes, indeed. It is my honor to be running the SRC award show now. So if you are one of the finalists, or one of the students that was in the final round of the SRC, please already start moving to the front so that we don't have to wait for everybody. I hope at least some of you are here. Yes, so how does this computer thing work? Right, so the SRC, the way it is run, we have run it the way that we've always run it. So there was a small PC that selected the submissions, gave extensive feedback. We ended up accepting all of the submissions after some rounds of clarification for some of them. Then we had a poster session yesterday evening that many of you attended, which we are very grateful for, and that where we looked at all of the posters and then selected 3 finalists for each of the 2 categories which we have. We have an undergraduate category and a graduate student category. And then today we had talks in the session just after lunch for each of the 6 finalists gave their talks, and then we put them in the order that we will now present. So the third place in the undergraduate category goes to Optimizing Asynchronous Rust with Hydroflow by Ryan Alameddine. The second place in the undergraduate category goes to Wonko, WebAssembly AOT compiler that supports live migration by Reiki Tamura. And the first place, finally, in the undergraduate category goes to Property Testing Trace Languages by Jetko Jin Kert. And this brings us to the graduate category, where the third place goes to Efficient Strong Simulation of High-Level Quantum Gates by Adam Husted Kjestrøm. The second place in the graduate category goes to System F Omega with Coherent Implicit Resolution by Eugene Flessel. And finally, the winner of the graduate category of the SRC POPL 2025 is the State Order Consistency Testing Problem for C-like memory models by Grace Tan. Pick a background. Oh, the sponsor, that also works. Okay, thank you everybody who was involved.
Hi. Yeah, so it's time for the announcement of the next POPL. So next POPL will be in France, in Rennes, the capital city of Brittany. So Rennes is 1 hour and a half away by train from Paris. And there are connections to Europe's major capital cities. So the venue will be located at Couvent des Jacobins in the city center. So it was built in the 14th century and recently renovated as a congress center that you can see here. So the website for POPL'25 is already online. You can have a look at it. And the organizing team is partly formed. So Suresh Yaganathan will be the program chair. Unfortunately, he was unable to come here today. So we also have 5 associate chairs as this year. And you can look at the website to see the important dates. So yeah, we hope that you will submit your best paper before July the 10th. And then come to Rennes to attend the conference. So if you have questions about venue, so please do not hesitate to come to see me and talk with me. Thank you.
Hi. I'm Jonathan Aldrich. I serve on the ACM Publications Board, and I just wanted to help spread the word about a really important transition that's going to affect all of us to some extent. ACM will be all open access as of the next POPL, in fact, as of January 1st, 2026. What that means is that all, yes. So this is indeed really exciting. I'm glad you're excited as well. All papers in the digital library will be freely available. Actually, all papers from before 2000 are already available, but everything's going to be open, which is wonderful. It's good for science. It's good for authors. Open access papers are downloaded more. I think 3 to 4 times more, and they're cited more, about 66% more. And in fact, you asked for this. There was a petition. I and some other SIGPlan members were involved in that. SIGPlan has, repeatedly supported open access in polls that were taken to the community. So I think this is a really great news. There are some things that will change, and changes can be disruptive, and so we want to just make sure everyone is aware of that. The financial model is changing. So the big thing that ACM is, the big ACM initiative is ACM Open. It's a new subscription model. Before, your library is subscribed so you could read ACM papers. Now the papers are available for free, but your institution now will subscribe so that you can publish at no extra cost to you. So about 2/3 of ACM papers are already covered. A lot of the papers in workshops and so on are already open access. Of course, everything in POPL is open access because SIGPlan has been supporting that. And some of you support that through ACM Open and through your own funding as well, which SIGPlan definitely appreciates. If your institution is not a member of ACM Open, though, there will be article processing charges. Currently, that's $700 for ACM members for conference and workshop papers. Importantly, there's no charge for short 2-page abstracts, student research competition, no charge for that, for example. If workshop gives a 2-page paper option, again, there'll be no fee. The other good news is that maybe your institution is not a member of ACM Open. Maybe you don't have grant money. I encourage you to put APCs in your grant money if you're going to need this. It's good to be open. But if you don't have grant money for this, you can ask for a waiver. And authors from low-income countries don't pay or get discounts depending on exactly how low-income the country is. Some things. So think about those transitions. It will affect, for example, workshop planners, conference planners, and other parts of SIGPlan. Encourage your department head or university librarian to subscribe to ACM Open. They may not know about it. We've been trying to spread the word, but tell them that you care about this. It makes a big difference. And finally, I welcome questions. I want this to work. I know SIGPlan leaders want this to work for the whole community. And so, any questions, any concerns, please bring them to us. Thanks.
All right, that concludes the official agenda for the business meeting. However, we always have a time for open discussion or questions if anyone has anything to bring forward. If not, question, yes.
I've been asked to stand up by Sasha, who is the SV chair, one of them, who was there when the flooding occurred. And basically, I'll say 2 things that he said to me. So one is about Naringa. Naringa, there was a pause in amongst all the problems. And in this 15 minutes pause, they ate chocolate that Naringa handed around and just chilled for a bit. And Steve and I know the qualities of Naringa, who always is looking after us at POPL as the program manager employed by ACM. But this is an example of why actually she is so good. And I also want to talk about, yeah, let's go. And I want to talk about Steve, supported by Stephanie. Steve, so I was general chair last year, and the reason why I took it on was because I thought in 20 years' time, I want to look back and say, yay, I did it. And actually, for Steve, just think about what happened. You had to step up in a way that you could never believe. And I gather you were absolutely awesome. Thank you.
And that's why this is such an amazing community. Thank you all. I hope you enjoy the rest of your POPL. And I guess, unless there's anything else, we can conclude there for tonight.